now heading, kind of up the takeaways from these experiments into talking about systems. One of the kind of pervasive challenges, I think, related also to the 2D video and linear audio challenge that I mentioned before, um, is the lack of kind of architectural metaphors and design patterns for this type of distributed AR. This is another way of saying the same thing, but that I think where we came to this and continue to explore it is that there is a focus on describing and managing the production process, the output, and that you could think of that even in a classroom, an interactive classroom environment, as the sort of compiled experience that's given with a instructor in a class. In our case, it's production versus rehearsal. In other cases, it might be sort of the difference between a simulation and final output. And that the sort of design patterns that we have are all on the way to what is the final output. And we found this even in the Unreal case, but in a variety of different tool sets where we're working on kind of shared XR environments, as opposed to the process of iterating on each individual element with multiple people working at the same time. So there are lots of practical things that can be done in revision control. There are certainly ways to collaborate in these environments, but at the same time, turning kind of the metaphors that, finding the metaphors that we could use to author within these distributed systems was one of the key challenges. All right, I'm going to go through a specific example here in a moment. All right. Oops. Sorry. So a particular example of thanks for the comment, Paul. I'll try to come back to that in the end here. So particular example of this in the spatial dimension was starting to think about constructing space based on observation of placed fiducials, which is nothing, I think, particularly surprising in augmented reality in particular. But we had to build some tools that would allow us to do reasonable AR tracking based on predictable elements of the production. And this, I think, if we think about where you're headed by the end of this experience, and you can see it as we go to the end of the video here, where you're headed by the end is to be able to take that 3D environment, overlay it on a real world scene and align it based on those multiple fiducials. But the sort of iterative and critical part of this is that by creating a mapping between the physical space and the virtual space through a set of fiducials, we imply the ability to move those fiducials around and shift the organization of the space in maybe an iterative or experimental process. So let's say that instead of doing this in the home, instead of doing this in a theater, we're looking at doing it in several different touring venues, or we're looking at doing it in a home in the context of an educational experience. So it's convenient to focus on the alignment of one space to another, but the sort of opportunity in terms of authoring and iteration is to think of a flexible construction of space that actually can change the relationship between these elements. And this is, of course, research that's out there in the AR world, but hard to operationalize. And I think a lot of interesting work can be done. And it sets one particular example of many in terms of the opportunities for iteration and experimentation. All right, I'm going to go through a little more quickly here and talk a bit about interaction. I think this will come back to some of the discussion of authoring in time as well as space. And so a consistent need across these projects has been to balance guided and free navigation. And we see this now looking at immersive learning in XR, which is where some of the extended reality examples that I gave. We see it in the augmented reality case, in the Man in the High Castle project, where People move from being a voyeur to a silent participant to asking to sort of participate in a moment of the production. That progression is a progression from being guided to having some flexibility to then suddenly being asked to take action that might interrupt or change the narrative. And that takes us out of timeline-based authoring and into something that looks quite a bit more like interactive storytelling or game design. But the techniques and tools to move smoothly in and out of those things are still relatively limited or completely customized, right? So it's easy to imagine writing quite custom game logic that allows these types of things to happen, but that runs counter to this desire to want to be able to iterate on the nature of collaboration in these experiences. What do we allow people to do? What are they constrained from? How do they come in and out of a kind of traditional linear experience and then head out into exploration and come back? Those are the types of things that we found ourselves really wanting to do. A couple other examples here that I'll hit on in a little bit more detail. The second is, I think, an interesting missing piece that's emerged a little bit in work by, I think, Rebecca Fibrink and others, where we're looking at how to teach interaction by example and train domain-specific machine learning. So maybe have a pre-trained model that can be tuned for a particular type of interaction relating inputs and outputs. This is the type of thing that we would like to be able to do. Follow this actor in the virtual space with a camera in this way and show that example live, and then be able to replicate important elements of that in other situations. And there are many variations of that. Kind of show something by example, which fits the rehearsal process and way of working very well. And then shift it into kind of a controllable automation. So there's a really nice opportunity there for interactions between kind of input-output pairs or input-output groupings that is less about supporting human-to-human interaction than the HCI relationships that are intrinsic to some of these systems. All right, and then the third, and I'll give an example of that in a moment, is the shift away from thinking of the mobile point of view in AR in particular, but in other areas as well, as the sole input to a system's understanding of the real environment and providing opportunities for interaction. So let me elaborate on that one, and then we'll go back to the machine learning one for a second. So these are some images from another augmented reality theatrical experiment that includes some large-scale projection. So that's what you're seeing is a physical theater, folks holding devices that have AR views and so on. And, you know, it seems like the types of interactive collaborative experiences that we're talking about often involve persistent experiences that are explored through end user devices. And the focus of at least consumer AR is generally how do we allow those devices to be intelligent and connect virtual and physical elements through their own point of view. But for us in this context, it becomes pretty quickly apparent that if somebody puts the phone away, looks in a different direction, isn't looking at the critical action, doesn't observe their fellow participant, there won't be complete knowledge of what's going on, especially if some people have devices and some people don't. There are environmental phenomena that are unpredictable. And so one of the sort of key areas of interest for these types of XR interactions, whether they're involving augmentation or not, is to look at how the venues themselves or fixed sensor networks, to put it another way, can supplement the point of view of a multi-user simulation. And I could go all the way back to this example, right? Is that we have a set of remote cameras on individual actors who are incepted into this kind of collaboratively created VR world. And in that case, right, we have not a lot of information about what they're doing or how they're aligned within their own world, how they fit in. And there's a very sort of nice and simple distributed computer vision problem where we could get much more information about that from these camera views. And if you go one step further and imagine those people remotely are also holding a device or have their own point of view or have an HMD or something else that is providing that kind of point of view out into the world, Um, this mixture of fixed sensing in their environment with user point of view sensing would give us a much more robust way of understanding how to work, and also for action to happen that is not seen, of course, by one device and seen by the other. But we don't see a lot of that capability in AR in particular yet. So this slide, though, harkens back to that middle point that I wanted to make, which are the opportunities for machine learning to kind of minimize the weight in the detailed work. And I used it to describe opportunities in interaction, but it's also an opportunity for scene alignment and other things as well. So here you see a couple of views of individual remote actors and single scene sort of experiments, putting them into the 3D environments. And we would like to be able to automate um, the relationship between these actors in the virtual environment. A ton of effort put in to align their spaces. However, it would seem you could do that with fiducials. You could do that with some type of automated image alignment system. But what we find is there were enough variables in people's homes. So most of these students lived or slept or worked, where they had set up these green screens, that when they went down and came back up, they might be different dimensions. They might have a different piece of furniture that's covered in a certain way. It's very hard to have kind of any type of predictable automation of what's going on in the environment. So, but it probably is a pretty straightforward problem to think about how to grab alignment in a more robust way that's dependent just on the position of the individual, and how to get that individual's 2D video aligned into the 3D world in the same way that it was yesterday, which are the types of things that are speed up iteration time, lower sort of cognitive dissonance about I was over here yesterday and now I'm over here, those types of things. So I think there's a lot of opportunities for ML support in interaction. All right, let me get to the next one and then we'll have time for questions. All right. So the last takeaway from this experimentation relates more to media itself and media carried over the network. And kind of 2 points to make here is that I hope it's clear in this community, but network native thinking is still not quite permeated into the way that we work with broadcast media in many, many circumstances. And what I mean by that is it's still difficult and resource intensive to carry broadcast quality media over IP networks. This happens in higher end studios in many cases, but is still a fairly substantial transition. And kind of more importantly, most of the media that we're working with is still thought of in terms of a kind of analog televisual way of thinking, a series of rectangular frames per second. And I think for this group, of course, thinking about real-time 3D environments and other sort of basic components of distributed collaboration today is already object-oriented, individually addressable, sort of synchronizable in a completely different way, and even personalizable at the end user. And there's a big gap between how we think about 2D media, kind of the evolution of 2D media into things like volumetric capture, and the way of working and thinking in 3D. And there needs to be some work on that. And so, I think the point for us on the film and television side is there really doesn't need to be any coupling between the subject of image capture and the notion of a frame, or even the ability to look in that frame for a piece of an image and manipulate it directly. So one of the sort of intriguing areas of crossover with other research is in data-centric networking, and specifically being able to encode and secure individual components of images, whether 2D or 3D, whether in time series or not, and access and manipulate them directly without having to worry about the channel or stream or pipeline that they're carried in particular for security reasons. And so to kind of wrap this one, I'm getting a note that I should start wrapping towards questions. So let me go ahead and do that with just one or two more slides here. So the question I would ask is, what about the intersection of 2D and linear media even including volumetric photography. Um, do we need new formats and strategies for networking that allows more addressability of components, allows some of the access in time and space that I mentioned earlier to be thought of even within a frame, and allows us also at the same time to move away from app-centric ways of getting and distributing content. So this is a longer discussion that's related to networking and network architecture research that's actually been going on, including Colorado State folks and others for some time. Um, but I think it presents a unique opportunity to sort of shift away from televisual and analog thinking in the way that 2D media shows up in these 3D environments. All right, and I can come back to that with some more detail later on if we want to do that in the questions, but let me sort of wrap up with a few points reflecting back on this work. So of course, it seems obvious, but it was really brought home by the remote experience and the idea of wanting to iterate quickly on shared 3D environments while people were physically separate when they were working on those. There needs to be research in this area that focuses on authoring ease and runtime editing. There's some nice opportunities, I'm sure some that are already being explored about machine learning, aiding that authoring and collaboration process, specifically through teaching by example. A lot of what we see in media and creative tools are image enhancement or image analysis, semantic understanding of scenes, but a little bit less about kind of input-output mappings in other domains that could really support interesting notions of interaction. Then I think this notion of managing layers of semantics, of overlaid ontologies, is a real opportunity, and we saw it, in remote spaces that become part of shared virtual spaces. We saw it in kind of more standard augmented reality requirements, and we see it in fictional storytelling and education and so on. And those overlaid and interwoven ontologies become critical to the authoring process. Um, I think I mentioned this and talked about it enough already, but this idea of the compile build step is related to authoring ease as well. And then to return to the last point, I think moving the media world beyond sort of 2D raster delivery and channel-based thinking is important. And we, I think, had already been headed in that direction, but we found the emphasis on remote video as the default way of working um, in the pandemic kind of brought us back around to a fairly limited set of starting points for capture manipulation of media that were in pretty tightly controlled ecosystems like the Zoom ecosystem, for example. So I hope these are interesting points for the workshop. We have about a little less than 10 minutes for questions or comments. I am not logged into Discord, so I hope somebody can post them over to
Uh,
Zoom.
yes.
Yeah.
Thank you so much. I think it was a great talk. I will read the questions from Discord. Um, Thank you so much, and we can go a few minutes more later, a few extra minutes if needed for questions. Uh, so let me. I just lost the score. I had it right here. I think. Let me get into it again. Uh, so I think Jeff, you had a comment, but do you have any? I mean, Jeff, I'm sorry, Paul. Paul Martin, you want to ask a question because I know you also had a comment. You were very interested on this while open Discord.
Yeah, so this is Paul. I'm speaking a little bit later. I'm with HP in Colorado, very close to Colorado State, by the way. Great talk, Jeff. Really, really impressive. Really, uh, really loved it. So I'm more in the commercial domain, as I mentioned, and I'm in the XR group at HP, and a lot of our customers are wanting to collaborate around more commercial things such as product design, architecture, et cetera. Given the worldwide nature of a lot of corporations, shifts in time in terms of project engagement are pretty common. And it would be interesting to know if there are any kind of takeaways in terms of, time invariant collaboration that you think might be applicable in broader space such as commercial.
Yeah, I think that's I think the one thing that was a challenge because I think with distributed teams coming in and out of these types of experiences, one of the challenges was replicating state in a sort of in any given version of the system for somebody that might be in a different time zone and come later. I think this is related to the question that you're asking.
Yeah.
And and so a missing piece of the tool sets that we had and seemed to be easily available was, you know, if you construct a system pretty quickly, as we did out of the different components that we talked about, and you want to replicate a state that you were in that XR environment and let somebody look at it, and it was dependent on too many steps beforehand, it became almost impossible. So a key feature of the asynchronous collaboration, you know, was the save game. So we did lots of kind of manipulation of the way that we used save games to pass um, state in between different iterations. But if we had thought about it at the beginning, we would have made that a first-class feature of the system to say, you know, what is a snapshot, and have I built my environment so that I can recall that state anywhere? And so somebody that has a copy of the game or simulation can recall that state. And it's non-trivial if there's also media present and other things. So that was really a key thing that I kind of mentioned it, but didn't quite get in the slides, that if we had architected the systems properly from the beginning, we would have really thought through how to replicate state in that way.
Yeah, makes total sense. Yeah, thank you. That's great. Another quick observation, maybe in terms of the less serial and video-oriented media distribution. Um, I don't think it solves all the problems, but USD, which is a universal scene description language, is being used, obviously been used by Pixar, now being used heavily by NVIDIA, for example, in Omniverse and collaborative 3D engagement. Doesn't capture all the elements, but do you see something like that as possibly being a component of a broader language?
Yeah, I think so. I mean, I think there are multiple. Seems like there are multiple challenges in the sense that one is how the media is described. The other is how it's carried and how quick. So I think the purpose of showing this slide, even though I went through it rather quickly, was even if one of these individual video frames or layers is described in a way that's more robust, or has more, is described in that type of way. If we put it inside of a channel container or way of thinking, we have to kind of ingest it or access it or decode, figure out how to authenticate to it, all those things before we can use it. And so some of what's appealing about a data-centric network fabric, network architecture, is to have those types of descriptions and then have them available at packet granularity or with some kind of indexing at packet or object granularity, that allows us to reach in and grab a frame at a given time and access those types of things in random access rather than kind of bundled inside of a stream. So it's more about maybe how they're carried on the network.
Got it. Yeah. Okay. Thank you.
Sure.
And a question from Discord. Thank you for thanks. They're thanking you for the presentation, and they're saying, what is the technique for chroma keying to remove background? Do you use depth cameras? How about the lighting after embedding into the virtual environment? And I can put it on the text if you want, but
I think I have it. So um, we would use any available background subtraction or background removal technique. So most of this is basic chroma key and pretty crude at that, just because the production value was not the emphasis of the projects. We're looking at more Zoom-like automatic background subtraction. Certainly, you can use depth cameras if you have them. We were not able to get, we had a couple $100s to equip each space, and so, or each remote actor, which is different than a stage environment where we might use depth camera. I think what was the second part of the question? Because that was interesting too. Sorry, Francisco,
yes.
oh, I
How
see it
about
now.
the
Okay,
lighting
lighting
after
after.
getting into the virtual environment?
Yeah, so this would be, specifically in the world of 2D or 2.5D compositing into these 3D environments, the ability to relight I could imagine maybe some clever ML techniques to relight uh, relight actor video based on the 3D surrounding environment. That would have been fantastic. In general, we were doing manual matching in camera to whatever we expected that remote environment to be, and there's lots of limitations for that. You can certainly do remote control, and some people have done this already, of the real world lighting, and so shift it as the virtual world shifts. But it would be more exciting to see some automated techniques for relighting 2D video. I haven't off the top of my head, but I could imagine there's an ML paper or something out there in that that could be applied. That would be really neat.
Thank you. Is there any other question anybody would like to ask? You can just say it or type it.
I have a quick question. This a lot of the stuff that you were talking about reminds me a lot of what was just happening with the Royal Shakespeare Company and Marshmallow Laser Feast Dream. I'm just curious if you had a chance to watch that production and look into that at all, and if that was, getting any additional insight, because they were also using Unreal Engine, but they were doing a lot more motion capture stuff with the actors and doing puppeteering. But I'm just curious if you generally were paying attention to what was happening with that, and that intersection between theater and these tool sets seem to be a nice playground to kind of do a lot of innovation. Just curious to hear your thoughts.
Yeah, I'm definitely aware of it. I haven't seen that. I didn't get a chance to see that live. I was hoping to try to find a way record it. I am aware of some of their earlier work on the Tempest, and we think that theater is a really incredible playground to push on some of these things, and a lot of the reason the theatrical projects have been valuable is the theater thinking tends to be immersive and omnidirectional and not frame oriented in the way that film thinking is. So I think, for this group, maybe that's part of what might be interesting about what RSE and the types of things that we're experimenting with and other theatrical folks, is just it's easier to get from, well, we're not creating a frame anymore, we're creating an environment, or we're putting characters into that environment. I think the only reason we haven't focused on motion capture, one is the upfront expense, at least at the time, before some of the new ML techniques, but also the haven't really sorted out the how to have an in-person and remote experience at the same time. And I think that's part of what's sort of interesting about the evolution of the available technologies away from marker-based capture, and also some of the opportunities to move away even from green screen production and other things. And I think I don't, it seemed like they had gotten to that point in at least the things I remember seeing from that production. So yeah, very, very related. We're probably we've stayed away from virtual characters um, because of how production intensive it had been. But with some of the new techniques that are coming out commercially for lifelike or fictional characters and things, we probably will do more with that. So super related and very interesting. But I haven't seen that particular show yet.
Cool. Thanks.
So thank you. We'll have one last question. If anybody has a question, I never thought of theater, but now that you mention it and you went through this talk, this is just a comment. I believe theater is great, even more if you have theater when you have a group of actors in one place while the other group of actors in another place, and there's all this interaction and movement of objects and pieces that makes it quite interesting and difficult at the same time. So with this comment, I want to know if there's one last question. We have time for one more quick question if anybody else has, and if not, we'll move to the papers. Any questions? All right. Jeff, I want to thank you so much for being part of this workshop, for presenting and letting us see what are your thoughts and what you're doing. So with that, I want to thank Jeff, and
Thank you.
then we'll move to the five papers. And after the five papers, we'll have a break. And And Ken, thank you for that text. Ken just sent some an interesting Twitter about some behind the scenes from the Dream clips from Dream. Um, so our first presenter is Liu Thompson, designing a collaborative virtual reality application to increase social inclusion among neurodiverse students. And I'll play the video, and once the video is complete, he'll take questions. Thank you.
Thank you. Hello, and welcome to the presentation of our workshop paper, Designing a Collaborative Virtual Reality System to Assess Social Inclusion Among Neurodiverse Students. I will begin by introducing the project and our motivation for taking this approach. Neurodiversity refers to variation in a human brain, for example within a group of individuals. We distinguish between variations as divergent or typical, while acknowledging that further work requires more detailed descriptors to understand the needs of our users regarding the design of the VR system. As of now, the following presentation will present and discuss the concept of enabling interaction between interpersonal relationships between neurodiverse individuals through collaborative play, which is partly defined as an individual's experience of social inclusion. Experiencing social exclusion has been linked to a decrease in well-being through stigmatization and discrimination, while the contrary, experiencing social inclusion, has been observed to result in improved happiness, self-esteem, confidence, and mental health. Another implication of a lack of inclusion in the context of school attendance is the decrease in social skill development. This consequence was of interest to the project group. How can we use VR to eliminate barriers to social inclusion and promote social skill development that may affect group dynamics experienced in real life? The project group consisted of researchers from the Multisensory Experience Lab and professionals from the Danish company Specialisterne, whose primary objective is to build bridges between neurodivergent individuals and the job market. To further refine this idea, we started to investigate traditional methods in the field to gain an overview of the opportunities that VR may present. Traditionally, the social outcome of inclusion interventions has been researched in the field of sociometry. Sociometry has been established as a reliable methodology to assess and map social relationships in a group. However, the method relies on self-reported social preferences found by asking individuals about choices in social situations. For example, who would you like to sit next to in the bus? We found this to be interesting as VR presents many more data points for observation on implicit behavior in social situations. We were interested in understanding how VR can support the training needs of both neurodivergent and neurotypical users. We found positive prospects on the use of VR to train neurodivergent users executive functions, communication, social skill development, and what is referred to as daily living skills training, an important set of skills of neurodivergent individuals to gain independence and increase well-being. We also found positive prospects on the use of VR to represent and interact with more advanced and abstract concepts in mathematics education, a task relevant to neurotypical individuals. Moreover, interesting research on group dynamics in VR informed us about the range of emotional states that users experience in VR, which was found to be similar to real-life face-to-face experiences. This phenomenon supports our premise that the social interactions and skill development in VR may be transferable to real life and thereby change or overcome issues related to social exclusion in a group of individuals. This led us to the aim of designing and implementing a VR system that allows neurodiverse students to engage in collaborative tasks of varying difficulty for the long-term purpose of studying inclusive behavior in a school class. We chose to combine the DLS training scenario of supermarket shopping with the balance model for teaching mathematical equality. Moreover, we implemented verbal communication through voice over IP and non-verbal communication through map body language using inverse kinematics. Finally, an additional support module was implemented in the shape of a wristband with two options for visual and auditory help sequences regarding the objectives and tasks of the virtual environments. This was done to allow students to receive help regardless of the situation and to log the potential support preferences of users. So, in regards to the situation at hand, we designed the collaborative task to involve several sequential tasks involving various types of products and shopping mechanics allowing users to execute the task. At the entrance of the virtual supermarket, users are met with a shopping list of 5 products. The products require 2 types of actions, either finding the product and collecting the right number, or measuring the right amount by using the virtual balance. This collaborative task was part of 2 additional virtual environments. As you can see here, the flow of the 3 virtual environments was as follows. Select avatar based on user preferences, introduce concept related to tasks of virtual supermarket, and perform collaborative task of shopping in the supermarket. 10 pre-made avatars were selectable by users. To visualize the avatar to users, a mirror was implemented, and in order to adjust the scale of the avatar to the users, a button for recalibrating height was implemented. When a user was satisfied with their choice, they could press the button for entering the virtual classroom. The virtual classroom was designed to resemble a traditional classroom and included props and concepts from the supermarket. The idea here is that a teacher can use this virtual environment to slowly introduce the elements of the collaborative task before entering the virtual supermarket. Additionally, a task pad was implemented in this virtual environment to introduce the use of the balance model to measure amounts and figure out the weight of objects through mathematical equality as the deflection of the balance pans depicts. Finally, we have the virtual supermarket. As seen on the 2 overviews, the supermarket includes different sections with different types of products, being the butcher section, processed food, refrigerated goods, and fruits and vegetables. As seen in the picture on the left, users were met with a shopping list depicting a thumbnail of the products, the number or amount, and the name of the product. Next to the shopping list, a shopping basket could be found allowing users to collect items for easy transportation around the virtual supermarket. On the picture on the right, the virtual balance can be seen. Users can measure amounts by placing weights on one side and products on the other. By reading the deflection of the balance, users can determine whether products weigh less, equal, or more than the placed weight amount. After determining the correct amount, users can place the fruits or vegetables in a plastic bags, creating a single entity of the product for easy transportation. Finally, after finding and gathering the products requested in the shopping list, users can approach the self-scanning register to scan, pay, and purchase the products. Here, users are met with a display showing the scanned items, the total price of the purchase, and the remaining price. A wallet with Danish coins and notes appears next to the register, and these can be dragged into the money slot of the register. If users make mistake, they can choose to clear the list or delete the latest scanned item. Finally, when items have been scanned, placed in the shopping cart next to the register, and the purchase price has been matched, users can push the pay button, and depending on whether the shopping list has been partially or fully completed, a rewarding sound and confetti animation will be played. Based on this design, we conducted an exploratory study with 8 users, being 7 neurodivergent students and 1 teacher, which highlighted several design issues related to the collaborative mechanics of the VR system. Although the audio or verbal communication was spatialized to attenuate direction and distance, users requested additional visual cues for the communication. This could be done by artificially highlighting avatars currently speaking, or to implement further facial expressions related to the speech output through mouth animation. These cues were requested by the users to easily determine who is talking at any given point. The VR system has a selection-based avatar system, which currently does not allow for fine-tuning to a user's personal appearance. We believe that future iterations of the system should extend this system to allow for better customization of particular features of the avatar, or perhaps implement an additional step in the VR system's pipeline, allowing teachers to take images of users and generate avatars. A number of commercial solutions are available for this particular purpose. The group of individuals that were participants in the test were all relatively comfortable and excited with the novelty factor of VR. However, it is our hypothesis that for other groups of neurodivergent users, reducing anxiety is a crucial component to the experience. We believe that safety measures such as proximity monitoring, as seen in VR chat, and environmental changes could be used to provide users with a safety mechanism in situations that they feel are uncomfortable due to the uniquely dynamic social situation that can occur in such an experience. In regards to measuring the outcome in larger scale future iterations, we outline how short-term effects on simple measures such as procedural knowledge and competency development can be used to assess the VR system's capability in conveying educational material to users with varying needs. As a result of the obtained knowledge and skills from the educational aspects of the VR system, we may also observe effects on neurodivergent users' experience of independence and well-being in regards to how their DLS have changed after the experience. However, as a main objective, the aim of the intervention is the social outcome. Here we are interested in how the VR system's data logging and mapping can be used to generate reports for teachers in various forms. For example, the obtained data of social and collaborative interactions may be reported to teachers in the form of a sociogram, which is a graphical representation of social relationships in a group of individuals. This outcome is therefore twofolded. How can this new insight be used by teachers to assess and intervene? And how can the effect be observed individually in regards to well-being from experiencing social inclusion after the intervention? The teacher's report obtained from the VR system can include multiple measures regarding the group dynamics and individuals of the group. As of now, we see them as social and collaborative interactions and as personal preferences and performance. We believe that rich social interaction may result in observable affective actions, such as gestural greetings, verbal laughter, encouraging instructions, and collaborative actions, such as handing over objects, role-taking, and so forth. Moreover, to emphasize and discover links between individuals, we may observe on other dimensions to these interaction types, for example, directivity of communication, frequency, and performance logs. As a request from teachers of the institution we collaborated with, there was also a clear interest in learning more about the participating individuals to further profile their behavior and preferences. We see this as an opportunity to use the support module to exemplify whether or not a user prefers auditory or visual cues while learning.
Sorry, I clicked the wrong button. I apologize. I'll continue sharing.
Cognitive load may differ. To observe the engagement level of individuals, we are planning a simple logging module that tracks and calculates the engagement of an individual in regards to their activity level. How many times do they grab objects of the environment, and how many times do they push buttons or other interactive elements? This may also be used to assess the role-taking of the individuals by planning out and designing particular mechanics to certain roles of the collaborative task. To conclude, we have presented a VR system designed to promote collaboration between neurodiverse individuals by combining DLS and math training tasks. Based on a preliminary and exploratory study, we presented initial findings depicting several design issues regarding the collaborative mechanics of the VR system. And finally, we presented our considerations on how such a system can be used to assess inclusive behavior and report findings to teachers to learn more about the individuals and group dynamics of a class. Finally, we see the future work of the project as follows. Firstly, we need to reiterate the design by overcoming the issues found in the first test. Thereafter, we need to embed and test the data gathering module for behavioral observations. And finally, conduct a larger scale long-term study in close collaboration with the class and their associated teacher. Thank you for listening to our presentation.
Thank you. I apologize. I was told that um, it seems that my Discord and Slack notifications are coming through the audio. At least I was told by one person in the audience. So I'll go ahead and correct that. I'm not sure why, but we'll go ahead and take questions. Thank you so much for the presentation. If you have any questions, please let me know. Um, if there's any questions here on Slack, but is there any question for the presentation? Yeah, well, people think about it. I'm going to check Discord again just to be sure that there's no question there. Any question? Just go ahead and talk, please.
Okay, so please correct me if I am missed, but have you talked about the measurements that you used for your paper?
Have I considered the methods, or what was the question? Could you?
The measurements.
Yeah, well, we only presented a rather preliminary study right now that was used to identify certain design issues with the first layout. So as I presented, we are interested in logging attributes of the social interaction between users to assess this inclusive behavior between the individuals of the group. So the paper presents quite a few thoughts on how we will incorporate a data gathering module in the application and the system. But for now, it was a rather limited exploratory study to look at the design and the user experience.
Thank you.
And I see a question about the network architecture. We use Normcore, which is a networking library for Unity to synchronize positions of avatars and objects, interactive objects. And yeah.
Thank you. Is there any other question? Faisal, is there any questions on the score? I didn't see any. Well, thank you so much.
No.
We're gonna move to the next paper.
Thank you.
So next paper, we have 4 more to go, and they're great papers. The next paper is titled Revisiting the Scene Graph as a Bus Concept, Internetworking Heterogeneous Applications Using GLTF Fragments by Dajan and Steve. And I'm gonna go ahead and play the video, and then they'll take questions. And I'm trying to fix the sound thing with the notifications. Thank you.
There was what kind of network architecture did you use? That's technical and
So this is the revisiting the scene graph as bus concept into networking heterogeneous applications using GLTF fragments project. It's a bit of a mouthful, but hopefully the presentation should simplify things a little bit. So my name is Jaspreet, and in fact, this was before we wrote the paper, this was an MSc project dissertation, and I was lucky enough to have Anthony supervise the project with me. And together Anthony and I are big fans of kind of online experiences and Fortnite and kind of all of these things. And, you know, one thing, as we surveyed the existing, distributed graphical applications, we saw that these kind of applications, they use application-specific messages to broadcast the state of the virtual environment to other clients on the network. And over the years, this has become a really efficient way of communicating information between clients on the network. But what happens is we rarely see two different applications, or two applications that are built in different frameworks. For example, Unity, something that's built in Unity versus something that's built on the web. These applications rarely interoperate. And what we mean by interoperability between graphical distributed applications, should I say, is that content is never really, or assets are never really brought into other environments or shared between these environments. And I think one of the reasons for this is that um, uh, the messages used to communicate state between these applications um, often have a lot of um, engine specific detail in the data structures. So, Unity might describe geometry in a certain way, whereas a different engine may not use an OpenGL layout, may use a different layout for the vertices of the geometry, for example. And so those are some of the challenges, and what has been used in the past to kind of fix this problem is um, um, ways of abstracting the scene using a scene graph. So I know I haven't really used X3D or VRML, but my supervisor Anthony could talk for hours about it. Um, standard X3D used a common scene graph data structures, and more interestingly, the paper that we directly cite in our title, scene graph as bus, uh, they use an approach called a neutral scene graph, um, where game engines could convert, or applications can convert their local representation of the scene into this kind of ubiquitous, almost you know this data structure that could be translated to and from applications. So you have these wildly diverse applications, but they all communicate using the same data structure layout, the neutral scene graph, what it actually is. And our goal was to revisit this. How could we use these latest game engines, these latest tools and technologies, and kind of communicate state? So we chose GLTF, um, and we tested this on three different applications. We tested in Unity, which is used to create AAA games, very highly popular engine. We used 3JS, highly popular web framework, and Python, which is a highly popular language in general. And we called it the Hyperverse protocol, the Hyperverse Transfer Protocol, should I say? So we built these applications, and each of these applications support sockets, with the exception of 3JS, which uses web sockets, but we can still communicate. Um, and what this means is that we can have a server which has some GLTF information, or some GLTF binary information, otherwise called GLB, and it can go to the server, connect to the server, and then the server will pass this GLB message of the entire scene. These messages are kind of what we talked about earlier, but instead of specific things to do with the actual application, they're more generic. So these messages carry a payload, and this payload is the GLTF information. Kind of running out of time, but these messages they either include the whole GLB file, the GLTF files, or they can include little snippets of it, or they could use translations. And if I just give you a quick demo of what we managed to do. So here we have a Unity application on the left, and there's a box that's moving. And what happens is that the actual environment is stored to a GLTF file, a GLTF binary file, should I say, and it is sent to the server, and the server then passes this onto a Python file, which is seen on a Python application, which is seen on the right. And what you kind of see is the cubes are being mimicked between the two environments. So we were translating the cube, and we were actually adding new cubes into the environment, and the other application replicated the scene, very faithfully. So one of the strategies we used is for the translation messages, we could encode each node within the GLTF scene description with a UUID, and then in this packet we could update the position or the scale, the rotation of this object within the environment and track it. And on the client side, we could just use a hash map to represent the scene graph and we could use the UUID to get elements from the hash map, object 3D elements, should I say, of 3D objects from this hash map, and it becomes a very highly efficient method of communicating if we're just using state. And slightly over time, but what we managed to do is develop a proof of concept distributed system that uses GLTF as a neutral scene graph, much like in scene graph as bus. We were able to, replicate game objects and move them around and improve upon our packet design, which you can read in the paper. And it's a good starting point, but I think there's a lot more work to do. And I think this project I think there's a lot of potential. I think Anthony as well. I think we think that there's a lot of potential for something like this in the future. And yeah, that's it.
Thank you so much for the presentation. Who will be taking the questions for this paper? Anthony? Okay,
Jaspreet is here as well.
great.
Hey.
So is there any, let me see. Okay, is there any question that any of you would like to ask here? And please just talk or use Discord or use the chat message. I'll start asking question. I'll start asking a question while we get other questions. So you said there's more work to do. Anything that you can tell us? What's next? What are plans? Whether you're doing them or you think someone else could do it? What's the next step?
Yeah, that's a good question. I think Anthony and I think, are particularly excited about having. So in the example we used Unity and a client that was built in Python, and it uses just a standard OpenGL renderer for the Python application. But I think something that's really exciting is how would two game engines, so for example, a Unity game engine and an Unreal Engine game engine, how would they interact using this protocol and this system? Like, how would their physics interact, and how would that system look like? And I think that's certainly something that we'd really like to do next.
Thank you. Okay, there's a question on Discord. I believe it's for your paper because it just came in. He says,
I have a quick question.
Okay, go ahead, please.
It's okay to ask here.
Yeah.
I'm just wondering, is that the things that you want to make a synchronization between game engine, for example, Unity, Unreal, and on the webs, let's say the 3.js, for example. Is that the goal, right?
Yes. Yes, anything that has a sort of graphics backend, and because the whole point of scene graph as bus is that it only translates the things which are rendered. So it's neutral to sort of how the language runtime or the specifics of the physics engine and so on, which obviously poses a whole lot of challenges, but it means that it can run inside anything. You could implement the protocol that we've got inside anything that essentially can support GLTF, which is effectively anything that does OpenGL.
Okay, I see. Thank you.
So I'm gonna go ahead and read the question. Partially was pasted there. It's two or three questions maybe. Well, it says, what is the primary goal of separating the update and translate packets? Could the translation be treated as just another type of update? That's one question.
Yes, good question. So I think originally we used update as a form of introducing new assets into the existing environment. So in the video, I was inserting a cube into the scene. The the update protocol kind of caters towards that, because when we start including new geometry, we have to start amending the buffers, the geometry buffers and stuff. So so that was, I think, how we implemented the update functionality was it was just a binary diff of the two GLTF or the two GLB files, and whereas translate is just a simple it's just a simple translation matrix for a particular asset or a particular entity within the environment. I don't know if you have anything else to add, Anthony.
Yes, it's really just a measure of compression, right? So an update can be anything. It can be a new texture. It can be, because it's just a piece of GLTF, whereas a translate is just for accommodating what often goes on, which is something very fast moving. And then yeah, you could invent all sorts of different packet formats for things that, if you care a lot about particle effects, you could write a particle effect updater, but that then comes into, so you can extend the protocol however you wish, and then you probably have to have profiles and so on about who understands what types of packets.
Thank you. And the same attendee asked follow-up, I think, to this question. What about objects that are not based in real-world physics? For example, magic portals.
I don't have an idea.
I'm not sure really either.
All right. So
yeah, if you've got a GLTF object that refers to something else which isn't in memory, you know, then it's very difficult. But so yeah, you need something else for that. Right. I can't think of a way of doing that in the protocol as is. Yeah.
And I do invite people during the break to chat in Discord for those that are able to do so, or ask questions later. Was one more question by David Gilbert. Unreal/NVIDIA are doing something vaguely similar using USD in Omniverse. Is there a main reason you went for the GLTF format as a scene description instead of USD? And I'm assuming that USD stands for Universal Scene Description, or so, yeah.
From my side, I think I was just more familiar with GLTF. I think it's quite popular now, right, on the web and stuff. So that's maintained by the Kronos group. So the API is very familiar if you're into graphics development. Yeah.
Yeah, GLTF is quite close to the metal in some senses. So one of the other reasons is that we knew that it didn't need parsing. So that is a big issue with network protocols that are quite general in nature, as you because JustBit is able to just index directly into buffers and pull data out. It may be the same in USD, but it's not as well supported as far as I understand.
Yeah.
But you could probably do the same thing in USD. Yeah.
Yeah, I was thinking of US dollars when I saw that, but then I said, well, it has to be your scene description. Thank you so much. How do I pronounce your name? Jasprit?
Yeah, perfectly.
And Anthony, thank you. And recently, Anthony's lab released Ubic, a nice chat VR application. So it's
do you know about that?
That one. So. If you guys want to check it out, you can send email to Anthony, or I'll post the link later to GitHub.
We'll talk about it later, Francisco.
Yeah. Thank you. Thank you. We're going to go to the 4 paper, which is going to be a live presentation, no video. Paper 4, towards a platform of smart city scale cognitive assistance application. And the presenter is going to be Thomas, thank you, Thomas. Thomas Crush, and you take it away.
All right. Sorry, I thought there was one more paper before mine, but
there is one more paper, but for some reason you're paper number 4. There is one paper after you.
Okay, that's fine. So just gonna check my audio is okay, and you can see my screen, yes?
Audio's okay. We can see your screen. Yes.
Wonderful. Okay, good. So hello, thanks for having me. I'm Thomas Rausch from the Technical University of Vienna. My background is distributed systems, so this community is quite new to me, but I'm excited to work more on interactive systems and bring in my distributed networking expertise in here. So this project is a larger collaboration between TU Wien, the VRWIS Research Institute, Columbia University, and Cognitive XR, which is an academic spin-off we're in the process of founding, of which I'm also the technical lead. So we're building a platform for smart city scale cognitive assistance applications. And I first want to talk about cognitive assistance applications in an urban context. So imagine you're riding your bike through the city and you're wearing smart glasses that show you an overlay with data from your navigation system. But it can also display a silhouette of a car that's about to turn the corner that isn't even in your field of view yet. Or imagine you're one of the millions of people worldwide who suffer from corneal disease, where an AR wearable with object detection can help you find your favorite yogurt in the supermarket. Or think of people with cognitive impairments that struggle to interpret emotional responses. So here you can see a prototype we've built that does AI-based emotion detection on a video feed, which is functionality that you could use to build an assistive AR application. So there are lots of other use cases like this, and there's already substantial research in the area. But what I want to highlight is that these wearable cognitive augmentation applications sit on two pillars, namely AI-based video analytics, so analyzing the video feed from the glasses. Obviously, for interactive applications, that needs to happen in real time. So using existing cloud-based solutions or on-device capabilities is often out of the question. And the second thing is real-time access to sensory data from the environment, such as cars being tracked, road conditions, things like that. And the foundation for these two pillars, which is what our platform aims to enable, is really this emerging paradigm of edge computing. Edge computing has its own research community, and there's lots of different application areas, but it plays a fundamental role for mixed reality systems. So here's Ken Perlin, case in point, talking about edge computers in his keynote at the Visual Computing Trends Day a couple of years ago. And here you can see the AR device is connected via low latency connection, 5G, to a proximate compute resource with a GPU that can facilitate these types of interactive applications. And our project, Cognitive AR, is all about the question of how to scale this up to a citywide system. So in our vision, edge nodes are distributed throughout the city. The nodes contain embedded AI hardware and sensors. And our platform handles the runtime management of these distributed resources and the applications running on them. We also provide client software that abstracts the communication layer, makes it easy for AR developers to access the system. For the infrastructure, we're building on ideas from existing smart city projects. This, for example, is the Array of Things. It's a project by the Argonne National Laboratory. And an Array of Things node is just a box that contains several sensors, a camera, some single board computers for simple computations. And there's a deployment in Chicago of about 100 of these nodes connected mostly via mobile internet. And we expand on this idea to include what we call multi-purpose edge computer clusters, which is a federation of small form factor computers with different computing capabilities. And our platform hides this federation, makes it look like one computer. Here are a couple of case studies of edge node distribution and density. So on the left side, you can see the Array of Things deployment in Chicago that I was just talking about, and the density of nodes per district. And on the right side, you can see the density of mobile base stations in my hometown of Vienna. So there's already lots of groundwork for operating a distributed systems like the one we're proposing, and lots of opportunity for this distributed infrastructure and for networking layers. So far, we have a design for the architecture and a few prototypes for individual components. You can find the details of the design in the paper. For the rest of the talk, I want to demo what we have so far of these two pillars that I talked about earlier. So one part is the sensory data from the environment, specifically the tracking of objects for where we're developing a system we call cyber physical object positioning, or CPOP. So here you can see a prototype of how you can use a CPOP to track the 3D position of an object. The top left is what the tracking camera sees, and the bottom left is what the user wearing the headset sees. And in this prototype, we use a regular RGB webcam attached to an NVIDIA Jetson Xavier NX, which is a small edge computer with a CUDA-capable GPU that does the object detection, depth estimation, and with the camera calibration, does the translation into 3D position. This runs at about 10 to 20 frames per second, and the positional updates are sent via Wi-Fi to the AR device. So the device is anchored to a common origin, which allows us to display the bounding box. But the point is that the AR device isn't doing any tracking. It's just receiving data from the environment in real time to do something useful with it. For offloading AI video analytics, so this is the second pillar, from edge devices to edge computers, we're developing a system called CogStream that enables the access to various types of AI services, for example, emotion detection. So first, the devices engage in a negotiation about the optimal streaming configuration, for example, the frame dimensions, the frame rate, compression quality, or which device does specific frame transformations. And then the edge computer simply returns the results from AI model inferencing frame by frame. We have some results in the paper that demonstrate how important edge computing is for interactive applications. Cloud-based solutions like Azure Cognitive Services, which already implement lots of these AI services, just have too much latency. But there's lots of existing research that goes into the performance aspect in depth. We're using quite a diverse tech stack. For example, we have protocol implementations for Go, Python, and C#, so that integrates with Unity. And you can follow the development of the project on GitHub. Everything is open source. So this is what we have so far. Building these types of platforms has lots of challenges that we're going to tackle in subsequent research. For example, dealing with uncertainties in object tracking and reconciling data from multiple sources. When we do AI-based video analytics for things like retail use cases, we have highly domain-specific models. So if you want transparent access, the platform needs to know, based on the context you're in, which one to use. In a citywide infrastructure, you have the issue of handing off communication from one node to another while the user moves around. It's not clear how well that will work. LTE base station handoffs, for example, can incur several seconds of latency, so that's not ideal. And also operationalization. So for example, how to streamline the calibration and anchoring of cameras if you have thousands of them distributed throughout the city. And a huge issue, of course, when cameras are involved is privacy, but that is a topic for a separate talk. So this concludes my presentation. If you're interested in our project, please reach out. You can find Cognitive XR on the web. Feel free to ask questions or to contact me directly. Thanks.
Thank you. Thank you so much, Thomas. So while we get questions, I have a quick question. If I missed this, I apologize, but where was your edge device in terms of a network compared to your edge? I mean, your edge server in comparison to your edge node, I apologize, in comparison to your edge device, which in this case, the HoloLens or whichever it may be. So how far was this in LAN? Was this outside of your LAN?
So yeah. So this is an excellent point. Actually, this is a broader point about the networking architecture and how the things communicate with each other. So in our prototype, they were basically in the same wireless LAN. So the edge node would expose. Actually, we had a small It's like a mini router, which just was serving as a wireless access point. And both the edge device and the HoloLens were connected to that mini access point. So that's very close range, 2.4 gigahertz Wi-Fi. We're going to experiment with other networking technologies. So obviously a big thing is 5G, and we're not sure entirely how well that will work. I mean, the promise of 5G is exactly to enable these types of applications. But it's the distance between the end device, the HoloLens, and the edge servers is a big open question. And since there's no real edge computing platform offering like you have cloud computing offerings today, it's not clear like how this communication will look like two or 3 or 5 years down the line, right? Possibly we're not going to use like any of these like really highly localized edge nodes that sit in some maybe smart lampposts or something. Maybe we're going to use we're just going to connect to our telco provider via 5G, and that's going to have, you know, a fiber connection to the closest data center that they have. So it's absolutely not clear how that will look, and we have to be flexible in terms of platform architecture to support, you know, whatever road telecommunication providers are going to take.
Right, because yeah, and I thank you for the answer. And of course, the distance will affect the latency.
Absolutely, yeah.
This work.
Yeah.
And when you were saying that we're not sure, this is a great question for to remind everybody that I posted the survey 1, I'll post survey 2, and we'll have a survey 3 for people that are not in the workshop. Um, Asking a lot of these questions, because one of the questions that we are trying to find out from the community is what would be useful to you to enable your research. And for example, it may be software stack, software or hardware or whatever it may be, edge nodes in different places. So feel free to answer those questions, and remember there's some great prizes for the raffle. And there's another question here. It says, have you tried, this is by Nico Felt, have you tried your setup in outside areas? Is the tracking still reliable?
We haven't tried it, to be perfectly honest, but it's the goal. So the goal of this, we got a small seed grant for this, and the first step will try to make it work inside, but the next step is definitely outside. I mean, HoloLens isn't a good device for doing these things outdoors, so we're going to get other devices, and once we have those, we're going to do the tracking outside. The models we use for object detection, they're trained for different environments, so they should work. The depth models, they're more complicated because they need to be trained on specific environments. And currently, the most of the depth models are trained on either the New York City, the NYU dataset, which is indoor, or the Kitty dataset, which is self-driving cars. So those are really both not environments that are designed for like outdoor surveillance cameras. So it's a big open question, but this is one of the goals, is to make it work. Yeah. And maybe I can just take Jeff's question, which is if we have a sense of how edge nodes might prioritize compute tasks, or is the workload statically configured? So this has been the focus actually of my PhD thesis, which I just completed, was how to allocate resources optimally for these types of edge workloads. And my experience is that there's a lot of fine tuning involved depending on the type of devices that you have. So the cluster configuration that you're using, and also the type of workloads and what they're doing and what type of resources they're using. But essentially what our scheduling system can do is it can figure out which workloads require which type of resources. So if you have a GPU intensive workload, it will schedule that on a CPU. And if you have one that doesn't need as much GPU and can work with the CPU, it'll do that. But this is like cutting edge research, and we need to figure out how well it works depending on the architecture or the infrastructure and the types of workloads.
Yes, and for content, I think you were answering the question by Jeff Burke that says, great talk. Do you have a sense of how edge nodes might prioritize compute task, or is this workload statistically configured?
Right.
That we're answering that question, right?
Yes. Yeah.
Right. So for content, because people, when they watch this recording or live stream, they may not have access to the chat. So
yes, yeah.
Thank you for that. Thank you so much for your presentation. Is there any other question? I'm gonna go ahead and believe it or not, I made a mistake. So uh, I did skip a paper. So you were right. So we're gonna go to this was paper number 4. So I skipped the paper number 3, uh, by Maximilian Kalush, a shared haptic virtual environment for dental surgical skill training. I'm gonna play the video and then he'll take questions. Thank you so much. Remember that you can continue the conversation either through this chat, or if you're registered in the Discord, we have a workshop channel that you can continue the discussion beyond the workshop and also while we're in break. So I'll play the next paper. Thank
Dentistry is a difficult profession to learn. Moreover, the required training resources are very costly. Each completing dentist student costs around 350,000 US dollars. This makes it one of the most costly health professions to train. And consequently, training programs have to be concentrated to very few places in most countries. Especially low to medium income countries, students might have to travel a very long distance. Not only equipment but also expertise is scarce. In our current times, we have all learned that online learning has become more and more popular, but the current options are limited to learning of knowledge and cognitive skills. Dentistry, however, is in large parts a practice of motor skills. Those allow a dentist to quickly remove caries tissue while minimizing the damage to healthy tissue. And VR is a promising approach to convey those skills, as it has been shown to help transfer motor skills. In fact, there are already several such simulators. To control the dentistry tool, a haptic device allows for natural input and force output. These high-fidelity simulators allow for repeatable training with very low operating costs. In this paper, we present a shared virtual environment for such dental surgery training. The shared environment allows a student and a teacher to experience the same haptic feedback. There are already several VR dental simulators, developed during research or as commercial products. The most sophisticated commercial systems, to our knowledge, are Simodont and Vertisi. They simulate the root canal opening with haptic feedback. Both use a stationary display, but with rather low immersion because of no head tracking. And both do not support collaboration. There are several relevant research projects, such as DentTeach, which was developed for remote dentistry teaching in a classroom style. So there's one teacher that can perform the surgery and multiple students that can observe via video. The surgery is performed on a physical tooth dummy, which afterwards needs to be discarded. Morris presented a collaborative environment for temporal bone surgery training, where a remote user would be transmitted the same force that the operator is feeling. However, they did not investigate the effectiveness of the system. Greenmora presented a VR simulator that shows a pre-recorded ghost tool that students are asked to follow, and they are rendered an inverted force. Suyin similarly taught students by rendering an opposite force. Kuchenbecker enhanced videos by playing back one-dimensional vibrotactile feedback. Now, in order to facilitate a collaborative environment, we first need a dental simulator. We developed a simulator in Unreal Engine that supports VR and haptic feedback. At the top you can see in-game screenshots that show the setup, and on the bottom you can see real-life photos that show the real hardware setup. There you can see an HMD is used to look around in VR, and a haptic device is used to control the dental drill. Given the simulator, our idea was to connect two PCs via network and each having an HMD and a haptic device. The system is divided in the master side and the slave side. The master side haptic input, PM, controls both local simulations of both the master and slave side. That way both simulations should have the same state. The communication between the two PCs is done via network to synchronize the tool positions and the haptic force. As you can see, the master is only sending data, not receiving. Thereby the system is unidirectional and latency cannot introduce a negative feedback loop, which is often the problem for remote haptics. The force on the slave side is determined by one of three different teleteaching strategies. The system can realize two different use cases. So on one use case, the teacher is using the master side PC and the student the slave side PC. The student here observes the teacher to imitate. The other use case is the reverse control, where the student controls the master and the teacher the slave side. And here the teacher observes the student so that he can correct the student. Teleteaching strategies are strategies to determine the force on the slave side of the system. We have designed three different strategies. Firstly, the same force, which is the most straightforward approach. The same force generated on the master side is rendered to the slave device. Now, normally, a haptic device renders the force that the environment is applying to the dental tool. For example, like you see in the picture, the tooth contacts the tool and will produce a force, Fm. Here, the position of the tool directly determines the rendered force. Contrary to that, the slave receives here a constant force that is unrelated to its position. Therefore, the user must counteract the force so that the device is near its center. Because of that, the user will have to apply the same force that the master is also applying in order to stay centered. The second strategy is very similar, just that the contact force is mirrored. So in that sense, to stay centered, the slave user will have to apply the force that the tooth exerts on the tool. Thirdly, the delta force strategy. This simply renders the difference of positions, similar like a spring, scaled by a stiffness constant K, and the spring points towards the master. So when the slave user gives in to the force, the slave system will be moved in the same position as the master, and thereby tracking its movement. Here it might become necessary to introduce a damping term if there are stability problems. As these two types of interactions are drastically different, so the user behaves differently, either he tries to stay centered or he gives into the force, we think it is difficult to combine these two types. Now, in order to realize such a system, we first need to have a robust dentistry simulation that supports drilling and at haptic rates of around 1000 Hertz to stay stable. We presented a simulation method that meets all of these requirements in an earlier publication. The foundation of that method is that it fills collision bodies with non-overlapping spheres, called the sphere packing. This simplifies the calculations and thereby speeding them up. And building on that, we need to update the mesh at runtime since we support drilling in our simulation. Here you can see the result on the bottom. The mesh on the right is generated at runtime just from the sphere packing. The visualization needs to run at interactive speed, and the carries procedure also needs to support vertex colors to display the curiosity. Therefore, we developed our own algorithm, which has 3 stages that run on the CPU and GPU. Now, firstly, we generate a distance field and a normal field based on the sphere packing. And for carries removal, we also generate a color field. Secondly, we run a bilateral smoothing kernel on all fields. This is done to remove high frequency bumps and other grid artifacts. Lastly, we perform marching cubes on the distance field. And during that, we do trilinear interpolation for the normal and vertex fields. And we implemented this algorithm with several optimizations to achieve around 10 Hertz at a resolution of 200 in XYZ. We implemented a comparison metric based on the distance field. To compare a given sample, we first need an ideal reference. For carries removal, an ideal drilling is of course just removing all the carries. For the root canal treatment, it is not as simple. There's no objective ideal, so we compensated by using an expert drilling. Based on a user sample and the reference, we can then use the comparison metric to compare both sets. We decided to use the dice coefficient since the tool is always samely rotated and has the same overall shape. We first need to define 3 cell counters, TP, FN, and FP, where the true positive counts basically the correct overlap, so all the healthy tissue that was not removed, and the both false negative and false positive count the error, so either the carries tissue that was left intact or the healthy tissue that was removed. And when we calculate S, we get a value in the range of 0 to 1, where 1 is the perfect result and 0 the worst result. Now, since we are not able to evaluate yet, to perform the evaluation yet, we will lay out our evaluation plan. Firstly, we make sure that all participants have a similar level of experience with haptic VR simulations, and then we divide them in 4 groups randomly. Each group will be assigned one of the 3 teleteaching strategies, plus 1 group that has no force feedback.
Thank you. That was the entire video. We'll take any questions. I'll start asking a quick question. Max, are you there?
Yes.
Yes.
I think the video was cut off, or
well, it was exactly 12 minutes. That's what I had.
okay.
If you have a longer video, feel free to upload it to the Discord.
Mm-hmm.
All of the speakers are welcome to do that if they want. So I'm not sure if there was something else coming, but what I wanted to ask you in terms of this instructor student, which I think is a very interesting problem, how do you deal with the what you're doing when you start working in a non-collocated place, meaning you have some students in different cities and you have the instructor? How does that come together? And if I missed that part, I apologize. I'm been managing all the chats and stuff like that. But how does that come together, and what is the future work for that? Because if we think about remote learning, I mean, this could be very useful, but then we start having the problems with latency and so forth. So any comments on this?
Well, we didn't test it out yet, but we think, like I said in the talk, it's unidirectional, so it doesn't have this problem that remote control has, where you get some sort of feedback back. So we think it should work fine with latency. But of course, you also need some kind of voice communication that we didn't build. So there's still some work to be done.
I understand. Thank you. Is there any other question that would like to be asked? All right. I want to thank you for the paper. We're going to move to the last paper. Thank you, Max. The last paper is using virtual reality to facilitate common operational picture representation. Aurelie is going to Cognes is going to present it. I'm going to play the video and then she'll take any questions. Thank you so much.
Hello everybody, my name is Aurélie Conges. I am a PhD student in the Industrial Engineering Center at IMT Nialbi, and I'm working with Penn State University. My research is a part of the Exercice Common Lab with the French company Immersive Factory. Today I'm going to talk to you about crisis management, common operational pictures, and virtual reality. The emergency response to a crisis, for instance a fire in a building, involves several organizations such as the fire department, medical services, or the police. Each of those organizations has its own chain of command, its own language to communicate, and needs specific information to make the appropriate decision. Some piece of information might be relevant to several organizations, but depending on their location during the crisis, it may not be available to all. It's crucial for all organizations to be able to communicate and understand each other to coordinate their response in the most effective way. This is not an easy task, which is why common operational pictures are implemented during a crisis. A COP is a display method allowing all of the actors to access, understand, and treat the same information about the crisis to achieve situational awareness. This is essential for clear communication and coordination of actions among emergency response organizations. COP are crucial to the crisis management process, but they currently have weaknesses. Today, they are mostly composed of paper maps and pins, and the communication is mostly phone calls. This induces difficulties for data analysis, even more so in large-scale crises with huge amounts of data. COP needs to show more than geographical data. Actors must also be aware of more abstract information, such as the available resources, the possible consequences of decisions, or even the weather predictions. That is a lot of data, and this can induce information overload. The information must be available to the actors who need it when they need it, but it must not distract other organizations. So to sum up, to be as efficient as possible, COP needs to overcome the following challenges. Display a huge amount of data in a readable and understandable way. Display geographical data but also more abstract data. And all of this must be done in real time and always up to date. We propose to use virtual reality and immersive analytics to overcome those challenges. Those technologies allow the users to immerse themselves in the data and viscerally understand them, for instance by extending the range of their simulated senses. The users are surrounded by the data. They can move around it, see it from different points of view, and interact with it using forces and gestures. This means that notions such as front or back can be used. We could place the more important information in front of us and push the rest behind us. Collaboration would also be enhanced thanks to VR, with users being able to interact with data in a single virtual environment, even if they're not physically together. We can find many examples of virtual or augmented reality for situational awareness or geographic information systems in movies. Minority Report, for instance, Avatar, Iron Man, or more recently in the Wings saga from Netflix. Outside of movies, VRGIS or VRCOP are not so common. They still present several advantages, such as a better visualization of the geographical data, an improvement of the associated decision-making, and new ways of interacting with GIS databases. Being able to observe a map in 3D from several points of view offers a better understanding of our environment. This, linked with relevant data sharing between several organizations or several levels of command during a crisis, would be very helpful for situational awareness and decision support. So, the virtual environment that we propose aims to improve situational awareness in a crisis context, in particular by improving COP representations. As stated earlier, COP usually consist of paper maps, boards, and post-its, and they are maintained according to data exchanged by radio or phone calls. Our environment provides a 3D and interactive map of the crisis location, which will be updated automatically and in real time through JSON exchanges with sensors or decision support systems, or even manually if needed. Let's imagine a crisis cell in our virtual environment. No more paper maps on the wall, they are replaced with a single 3D map in the middle of the room. The decision makers from several organizations are standing around the map with a global vision of the situation. They can see each other, communicate with each other, and interact together on the map. If they need to take a closer look, no need to find a more precise map. They can just zoom in on the 3D map. They can even jump inside any available 3D model of the buildings involved to see for themselves what's going on. The available actors and resources are in toolbox in the room. They can be placed on the map automatically or manually by grabbing them and placing them on the map. As soon as they're on the map, their location is registered as a JSON file ready to be sent out to the on-site actors or decision support systems. Various sensors on the crisis site are connected to the environment, such as presence, heat, smoke, water level, and they are sending information that can be displayed on the map as soon as received. This means that a replica of the crisis can be seen in real time on the 3D map of the virtual crisis cell. We talked earlier about information overload. In the virtual crisis cell, each decision maker could have a designated role that would act as a filtering system to only show him the data that is necessary to him. So not all of those functionalities are currently available in our environment, so we are going to keep working on it to implement them in the next steps. First of all, we want to connect our environment with RioSuite, the decision support system developed in our lab. In a crisis situation, given the necessary data about the context, resources, and objectives, RioSuite can provide a BPMN process of how to best solve the crisis. Let's imagine that this process could be available in the virtual crisis cell. It could be floating above the map, each task pointing to the concerned actor or location. This would allow decision makers to know at first glance if actors were unoccupied or if location of the crisis sites were neglected. We can also imagine that an urgent task would be more visible and that they would start fading away as they are being completed. We want to implement several functionalities, such as the detection of divergences, to show differences between the expected evolution of the crisis and the actual evolution of the crisis. We also want to implement anticipations to be able to visualize possible evolution of the crisis. We want to allow users to record what is going on in the environment to be able to rewatch it and see what worked and what didn't. And we want to use immersive analytics to allow the users to explore and analyze the huge amount of data gathered during a big crisis. To conclude, I would like to show you a video of our prototype at its current stage. As you can see, we have a 3D representation of a city. Here it is Seattle. This prototype is able to send and receive JSON files and to display the information registered on those files. We can move around the map, zoom in or out, turn the map to be able to see it from different angles. We can also add pins representing the available resources, such as policemen in this case, and those pins can be moved or deleted if needed. We are currently working on adding functionalities to it, but we believe that this will lead to a new way of presenting common operational pictures that will improve the decision-making process and crisis management. Thank you for your attention, and if you have any questions, I will be happy to answer them.
Thank you. Do we have any questions?
So I have a question. I don't know if I missed it or not, but did you use Mapbox for your simulation? Because it was similar for me to that tool.
We used Microsoft SDK for Unity, so it's yeah, it's similar.
Okay, can you please send it in the chat and then I can check it as well. Thank you very much.
Sure.
Let me check Discord. Is there any other question? I think someone is typing a question, so any other question, and feel free to speak up as well. Just give it a minute.
Okay, can you hear me?
Yes, we can hear you. It's a little low, but we can hear you.
Yeah, sorry, I don't have a webcam on this computer. So thank you for your presentation. I have a question. I don't know if it's in your next steps, but have you thought about sending information when users are clicking or interacting with your COP to the process of crisis analysis? What I mean is maybe it will be able to create some training exercises when you have some decision makers or users around the table, and they can act on the crisis, and they maybe can have some real information about their performance, if they have taken the great decisions or not.
Yes, in the next step, we are going to link our environment with, well, either a real crisis if we can, or at least with virtual environments in which we are going to implement crisis exercises. And so we will be able to communicate between these two environments and see what's going on our map, and see on our map what's going on in the virtual environment where the exercise is being conducted, and in the other way around as well.
Okay, thank you.
You're welcome. And to answer for the question, is this?
Let me read the question. Is the system intended to be used by multiple users simultaneously, or does every user sees a separate representation of the city map?
Yes, so the system is intended to be used by multiple users. There will be, for example, the chief or the policeman and the fireman, for instance, and they will be able to see either the same map, or they can have a filtering system to see only what concerns them, so that they could all control their own view.
Thank you. This is the, we're gonna go into a break now. We're gonna go into 17:10 GMT. And then we'll go into the panelists, which is Anthony Stidpo, Martin and Greg White, and then we'll have a Q&A. Then we'll have a break, and after that we'll have our closing keynote. So we're gonna have a break now until 5:30 GMT, which, if I'm not mistaken, will be, well, what time is it right now, GMT? I think it's
4:36.
All right, yeah, 4:36 GMT right now. So we're gonna go all the way to 5:30. So you have plenty of time if you know, I don't know where you are, but if you want to have breakfast, lunch, dinner, or just relax, use the Discord to talk to people. You can use the chat. We'll have a loop here showing you what's coming up next. I want to remind you for the survey 1, I'll be releasing survey 2 later. If you want to do it, we'll really appreciate it, and it's great prices. And I'll be releasing a survey 3 separately outside of the workshop for people that didn't come to the workshop. And I wanted to mention 2 quick things. We're hoping that if IEEE VR let us do it next year, we want to have this workshop again, maybe have more research papers. And there's 2 books that are very useful, I would say. Not one of them is the augmented reality book. These are not my books, so I'm not trying to sell anything. Augmented reality principle and practice by Malsteak and Hollerer. It has a chapter on collaborative environment, which is very good. And there's another a book called Immersive Analytics, and it has a chapter of collaborative environments as well that may be useful to some of the people in the audience. And I'll post the links later. With this, if you're a panelist and you want to test, and if you're the closing keynote, I don't know if Mark Billinghurst is here right now or not, but if you want to test, please feel free to test. And then after the testing is done, Faisal will put a looping PowerPoint showing what's coming next. Is there any question? Yeah, I'm getting a question. I think I made a mistake. I think I was trying to give myself too much of a break. I apologize. The break goes up to 5:10 GMT, so you don't have that much time. 17:10, 5:10 GMT, 11:10 Mountain Time. So I apologize for that. So we're gonna come back, try to come back a few minutes before 5:10. So that would be 30 minutes from now. Is there any? So 30 minutes from now. Yes, I apologize for that. Any questions or comment before I go? Anything that you may need? Well, I want to thank you. I want to thank the speakers for the papers. Thank you so much. I want to thank again Jeff Burke for the opening keynote. It was great, and all the questions, and continue the chat as we go. Um, Thank you, and Faisa, can you coordinate the testing? And I'll be back in a bit. Okay. Thank you. Thank you all. again, I want to thank Jeff Burke for his great keynote and all the authors for the 5 papers. Is we're going to have 3 panelists, and the idea is for them to give a small presentation in the theme of distributed collaborative environments, and then we'll have a Q&A. And while I will moderate the Q&A, ideally, what we want is really questions from the audience as opposed to from the organizers. So I would appreciate if you have questions, the panelists will be looking forward to answer them. So I want to introduce the 3 panelists before we start, and then we'll go on that order. So my first panel, the first panelist of the workshop is Dr. Anthony Steed. He's the head of the Virtual Environment and Computer Graphics Group in the Department of Computer Science at UCL, University College London. 25 years of experience developing VR and other forms of user interfaces. He's been in the community for a long time, as you can see, with the years of experience that he has. And he received the IEEE VGTC 2016 Virtual Reality Technical Achievement Award, which is extremely prestigious and given to people in our community. So I do want to thank Anthony. My next panelist is Mr. Paul Martin. He's the Chief Technologist of the HP XR Business Unit, located here in Fort Collins, Colorado. He started HP 36 years ago, when he was probably like 5, as an electrical designer and one of the industry first 3D graphic accelerators. Worked on multiple stuff, graphic systems, cloud computing, virtual workstation, and so forth. So we're really glad to have him, and he has a bachelor's in science and electrical engineering from the University of Colorado at Boulder, I would assume, and a master in electrical engineering from Stanford University. So thank you, Paul, for being with us. And last but not least, we have Dr. Greg White, the Distinguished Technologist at Cable Lab, technical leader who has been instrumental in developing multiple technologies, and he has been involved with quite a few projects, and we'll let him talk about this. And he's been leading this in this standards arena, actively promoting ANSI STC standards based on Cable Lab specification, and he has served on multiple standard committees, including the European Telecommunications Standard Institute, Cable Technical Committee, and others. So with this, I do want to thank the 3 of them. We do have ample bios in the website. I'll post the link again from each of the panelists. And again, thank you so much. So I'll stop sharing now, and Anthony, you can take over, and you can give your part. We'll move to Paul, then we'll move to Greg, and then we'll do the Q&A. If there are quick questions you may ask, but ideally we'll hold them, all of them, towards the Q&A session. Thank you, Anthony.
Okay, so hopefully everybody can see that. Those slides.
Yep.
Yeah,
Yes.
Great. Okay, so thanks, Francisco, and thanks for asking me to give a talk about some of the things that they're doing in research. And I thought I'd start off by telling you about some of my biases in this area, and then get on to some sort of simple things we're doing, and also make an announcement about something that we've just released, which I think some of you might find interesting. Okay, so so my biases. So I spent most of my postdoc years building distributed interactive systems, which were pretty sophisticated. This is the DIVE system, which is older than some of you on this call. But it was a sort of interactive 3D virtual environment that was multi-user, multi-party audio, in some ways more sophisticated than some of the social VR systems that are out there now. It had N-way spatialized audio. So 20, 40 people in the audio was not too much of a problem. It worked on multicast backbone networks and did things that are quite sophisticated, like mixing audio in the network routers and so on. So this is but it barely worked, and it only worked on university networks. So those of a certain age will know that there's no such thing as the multicast backbone anymore, or at least it's been replaced by sort of application layer peer-to-peer networks. But it's sophisticated, and there is a lot of functionality in here. So for example, when Jeff talked earlier about live editing the scene, this was live, right? I mean, you can edit as you went. It was all based, you could change the scene graph, you could edit the scripts whilst it was running. It was based on an old language, which again, most people will not have used unless you work for Cisco, called Tickle, which was designed to be embedded into large complex software and run as a sort of glue, scripting glue. But it was a nice system. So I got really interested in why these systems were like that, and got into operating systems and got very hands-on. But one thing that really happened is that network games took the research away from us, in the sense that network games, early network games were very unsophisticated. But around this time, I've put Burnout Paradise in because I spent one of my sabbaticals at Electronic Arts when this game was being finalized. I didn't work on this game, but I had lots of nice chats with the engineers that put the networking into this game, and exactly how they made it work. So how did they make it reliable on broadband networks of the time, at the late 2000s? So again, there's a lot of very, very specialist engineers, and to some extent, as Jaspreet said earlier in our talk, this game works simply because the engineers sort of really understood which bits had to be very reliable and which bits aren't. And they made there are some very gross assumptions in the networking for this game, and similar games where you think everything's synchronized, and it's not. I mean, it's an illusion that these things are synchronized. Anyway. So all of that led to this, led to me getting very frustrated with networking and writing this book that explained what I was frustrated about networking. And it's already 10 years old. So it's already a little bit out of date on some parts of what the networking is about. So the first bit, the first bias then, is what's wrong with the internet. And this is a whole hour in itself. So I'll just give you the keywords for that. One is that the types of thing we're trying to do with VR are fairly unique in terms of how the internet is architected, or how networks are architected. They are, the audio video streaming or web browsing is not the main activity. The sort of movement of 3D objects is the main activity. And some information changes very quickly and can't be buffered. So there's a lot of work in the past around sort of synchronous and asynchronous networking, and reliable and unreliable networking. And eventually, when you get down to it, one of the problems is that everybody comes up with a slightly different conception about what it is they're actually trying to do on the network. But it's sort of, there are protocols you can use, but practically every networked application I've ever seen has been very different underneath the hood, and about how it makes choices about this. And that hence what one of the idea behind Jaspreet's project earlier was, well, what if they did want to network multiple applications together? What is the model of having a lot of different collaborative projects together? Because there have been strategies for doing that in the past, right? I mean, there's been protocols at the sort of VR level that they're sort of in scene graph as bus, but I could enumerate some other ones as well. So what's wrong with the internet? It's built to move bulk traffic, but not to end-to-end speed. You can't reserve bandwidth except in limited cases. but I can argue about that later with somebody if they want. And it just wasn't really built for synchronous experiences. Now it's sort of streaming is one thing, but not bi-directional synchronous experiences. And one of the main things there is latency. And as if you've heard me ever talk before, I usually will go on about latency. But so networking is a problem, but I think there's a bigger problem when it comes to building collaborative experiences. And the bigger problem is these things. And they all impact what we do in different ways. So, for example, we love and hate Unity and Unreal, right? They help us build our games, and in this community, I can just make the point, and hopefully people will nod, that they're not game engines. Well, they are game engines, but they're not just game engines, they're production engines, right? So that, and there's as much in Unity about building the game as running it. It's more about building the game and running it. And so the question about how do I make a sort of collaborative virtual environment is not just when it's running, how do I synchronize things, but where do I inject collaborative content into this pipeline so that it has some representation in the runtime that I can then get my hooks into. So that's one thing to point out. The second thing to point out is all the the four things on the right, more to the right, which is that if you want to release something, you go through an app store on almost all systems. And I haven't put Oculus on there, but they're all, our experience of these applications is gated through somebody who ships a development environment, a runtime filtering environment to us. So the one thing that you can't do, for example, on the App Store is run dive, right? Because it violates one of the principal assumptions of the App Store, which is no interpreters, the Apple App Store, right? So there's very specific things that aren't allowed on the App Store because they can corrupt the experience. And one of them is running interpreters, with one exception, of course, which is the web browser. So there's a lot of constraints that come from this without, and if you're running experiments like my lab is, that when we're running experiments, we're either shipping zip files to people to run on their desktops unprotected, or we're sending them packages through SideQuest. And none of those four people on the right really wants to talk to us about how to ship a VR app to test, because we're so small scale, right? We're just you can't really live in their ecosystems and be researchers. Okay, so I said most of that. There's some obvious other things that I like to go on about. All these apps are sort of closed systems. That once I've shipped you a VR or an AR app, it sits on its own little bubble on your device. And I know some people at Niantic, and I keep going on about this, that this example of Pokemon Go being a map, but useless as a map, unless you know where you are, because it doesn't draw the street names. You can't put a little marker on saying I'm going here. You can't get the directions out of it. So if you're playing that game and want to go somewhere, you have to have Pokemon Go up and a map. And the game itself isn't even self-contained, right? I mean, it's not. You can play, if you play it around where I live, you'll go down a cul-de-sac, like a dead-end street, if you're trying to head towards something you see in the distance, because you have no idea if it's actually reachable. So if you want to reach it, you have to go to Google Maps. So why is that? And is that going to be the future of AR? So the core problem is that real-time and latency. So underlying one of my things here is that there's a problem, which is code, which I'll come back to in the last part of the talk. And that's the point I really like to talk to people about is there's a core problem of, if I want to make a really interesting distributed system, I need to send you bits of code to run. At the moment, it goes through an app store. How do I get you new code? Well, I can't send you scripts. I can download a new executable to you. And there are systems that used to do that, right? So there are systems that we used to be able to reprogram on the fly. And there are some attempts now coming back. So you'll see in the sophisticated sort of social VR systems, they've acknowledged this problem of how do you enable sort of users to modify things without sticking things into their Unity production pipeline. Because I think Rec Rooms built in Unity, I wouldn't be held to that if anybody's watching this online afterwards. I might be wrong, but I think it's built in Unity. So if you want to change a script, you have to get it into their build system, which is a pain in the neck, right? So, so they have this thing called circuits, and we've done a little playing with something similar called Udon in VR chat. These are solutions to a problem of how do you distribute an interesting, complicated VR setup. And is the web a solution? So I've just put that up just for debate later if we want. Okay, so what are we doing? So what is so manageable problems? So one thing. So one thing that we have done and we've released yesterday. We were just running around last week trying to get permission to do this from UCL. Is we've released a toolkit which solves some other problems in social VR systems. It's completely open source in particular, and solves a particular problem for Europeans in that you can run your own server. That has caused us unending problems with many of the social VR systems out of here, which all use data centers in the US, which means they're technically illegal to use for teaching and research in Europe. But I'll happily debate that with anybody. So we released a system yesterday called UBIC. We've been using it for about 6 months. We've been using it in teaching last term, and so there's and this is the final sort of demo yesterday where we tested that everything was properly working once we integrated all the latest patches. And this will enable. This is a Unity system for building social VR systems. It's out of the box experience. If you were to just run it, you would connect to a server at UCL. Sorry, I might not have been able to hear anybody for a while because some headphones have broken. And it would just run, and you'd be able to connect to this world. And if you want somebody to join you in that, you're welcome. It's open source and it's under the Apache license, so you can do what you like with it. So it's built on some experience in some recent projects on how to do the networking in a fairly easy way. It's got built-in audio using web standards, and we're for anybody who's got any experience with that, we're running turn servers to bridge connections, and we're currently going through porting some old experiments to it, so that some of our old social VR experiments will be open source, which is partly enabled by Microsoft open sourcing the Rocketbox. And then over the next few weeks, we'll be releasing some more complicated games, actually built by some students, and we'll be doing a Rocketbox, Movebox integration demo, and then doing one of my favorite things, which is sophisticated logging of the system, so you can get it into person synchrony of actions, and doing some remote, building some systems that show how to do remote experiment patterns. So these are motor user systems with individuals that have more power to control the system. And then finally, I'll just talk about 3 research directions. So these are things that we are poking at various research efforts. UBIC will remain our sort of platform for development, and we'll push some new features into it, which I think will be really very interesting. We do have this sort of Ether is not related to UBIC, and I have talked about this at IEEE VR before, but it's an attack specifically on the code problem. So how do I download code? So we have a working prototype of something we call the deck and the zone feature, which is downloading and patching Unity executables after they've been released. So this is again specifically to something that Jeff mentioned earlier and that we've encountered in the past. Is the one thing you don't want to do 10 minutes before a show or a demo is patch everything. You know, the number of times I sit around, my son asks me if he wants to play Fortnite, and I go, sure, yeah. And then I sit and have to wait for a 10 gigabyte patch to download. Goodness knows what they're doing when they're patching. This is the idea that you download a sort of big in client and then you download code. And obviously we can have a debate about is that secure or not, but it's using features of that Unity itself doesn't exploit inside the C# language, such as dynamic late binding. And we've architected the Unity pipeline so it can compile scripts so that they can be late bound through a DLL and just work as you expect. The second thing that I'm working on, which is with a student, and then actually is subject of a big proposal we've gone in at the moment, is something called behavior vignettes, which is trying to solve predictability for VR systems over the course of a few hundred milliseconds. And that's related to something that we will be talking about later this week, which is very tight synchronization between VR clients of the order of milliseconds to tens of milliseconds. So if I can't send you code, what can I send you that you can run for 100 milliseconds or 1,000 milliseconds to predict the future so that you can get a nice synchronous and conflict-free experience. So that's really interesting. Sort of, if you know, dead reckoning on steroids, right? So if you know about that technique, how do you extend that to something that is interactive? For example, how do you include collision detection in it? Because I haven't seen a system yet, and this is one of our test cases, is how do you predict space-time curves for things which actually have choice decisions in them? And if you can do that, then you can potentially make a nice, interesting distributed system. And then what we are talking about later this week is synchronization. So this is sort of proving that the way that game engines do synchronization is wrong. So client-server synchronization and authoritative servers is not the right way to do it. And so we've been, like some others, looking at this edge case where you have multiple clients and co-located, and Sebastian Friston will be talking about presenting a paper on Tuesday, quality of service for edge physics simulations. And at roughly the same time, another one of Sebastian's papers just come out in TVCG, which is a new approach to networking for VR systems called consensus-based networking. And so those are some of the things that we're doing. And that's it. The conclusion is the tools are improving, the ways are going, and unfortunately, it looks like I didn't save. There was a list of things underneath there. It raises a whole bunch of issues and operating systems, languages, and there's an opportunity to involve some really quite broad spectrum of systems engineers in thinking about how we actually architect these systems, because underlying all these network systems is actually, as soon as you get comfortable with that, you start wondering about the operating system and is it getting in the way, and is it architected for what we want to do in VR? And you start getting even more frowns, wrinkles on your forehead, scrutinizing things. Okay, I'll stop there before I mention too many different things.
Thank you, Anthony. And I think this is going to raise a lot of questions when we go to the Q&A. I would say that Anthony was raising interesting questions, that is things that we're trying to do with the survey, which is, as researchers, what do we need to make certain things happen? And because we have a lot of, problems, if we don't have access to the source code, like things are in the cloud, like spatial anchors from Microsoft, or not being able to run scripts because Apple or Facebook or Google will not let us, and so forth. So think about those things as we go into the next one. And now, Paul Martin, thank you.
Yeah, thanks a lot, Francisco. And I'm going to pre-apologize for my presentation. It's fairly corporate/marketing looking. Hopefully there are a couple of interesting nuggets a little bit later in the presentation, so I'll try and get there as quickly as I can. So thank you very much again for having me. And I was going to just talk about a little bit of history first, and I think almost everybody I've seen on the call probably knows this already. but just in case, wanted to step through a few things. One is, the immersive technologies are clearly not a new discovery, and Anthony, you know that very well, being in the industry for a long, long time. But one could argue it started with either this guy or possibly a little bit earlier. Ivan Sutherland was at Harvard, then the University of Utah in the mid 60s to early 60s even. He wrote 2 papers. One was called The Ultimate Display, page and a half, and described essentially the Star Trek holodeck and all the experiences you could have there. And then, wanting to get onto something more practical, he and a bunch of grad students started to create a head-mounted 3D display that actually puts you into this world in some sense. And it looked like that. It was a nickname, the Sword of Damocles, because it looked like, I think those are ultrasonic tracking elements. If they swung down, they would remove your head neatly. So hence the nickname. And just wanted to also comment that a lot of his grad students, so people like Ed Catmull and Jim Clark, et cetera, went on to really pretty much define the world of 3D graphics over the next several decades. There were other people involved a little bit later in time. Obviously, Cher Wang at HTC drove the development of the Vive after a chance encounter with Gabe Newell at Valve. And there's Jaron Lanier, depending on the continent. And he coined the terms that we use today, a lot of the terms anyway. And then prior to all that, there was even Tom Furness, who was sometimes known as the grandfather of XR, and who's still pretty active in the industry now, especially around the topic of immersive and education. So a lot of really, really smart people have been working on the problems for the last 50 years. And as a result, several years ago, we got these wonderful new VR devices, the Oculus DK1 and the HTC Vive. A little bit later in time, we get things such as the Oculus Quest, and of course, as some of the HP gear that I must represent, but also things like the Microsoft HoloLens and HoloLens 2. Okay, and really, these devices came about as a result of amazing advances in technology. So if you look at the graphics performance increases over that time period, just been orders and orders and orders of magnitude. As Francisco mentioned, I actually worked on a 3D graphics accelerator when I first started HP back in 1986. No, it was 85, sorry. And since we were able to do, I think, 3,600 shaded quadrilaterals a second, now we're up in the billions, of course. But some of the other advances have been closely associated with the mobile environment. So high-res displays, sensors of various sorts, including accelerometers, but also cameras and so forth. And then computer vision algorithms have all made huge improvements in this period of time. And then, finally, the love-hate relationship you mentioned, Anthony, with the existing content platforms. I think we're glad they're there, but yeah, they're not perfect in all ways, of course. Okay, so again, I work for HP, so we make a business out of this, and the segments we look at are commercial. Although we have been selling a lot of our latest headset, as it turns out, into gamers that, especially playing Half-Life Alyx. But these are the segments we look at kind of for the commercial sales, and you're the ones you'd expect, product development and architecture. And on the architecture piece there, that's actually our headquarters, not our headquarters, but our facility in Spring, Texas, that we just designed and then put in VR so the people that were going to use it could see it ahead of time. But also training, location-based entertainment, which has taken a bit of a hit in the COVID era. And probably most importantly, from a societal perspective, healthcare and education. So I'm going to drill a little bit on education in a few slides here. Okay, and one thing to note is all of these are great candidates for collaborative environments. You can see that in some of the photos here, but pretty much all of these will benefit for the end user if they're in a collaborative situation with somebody else. Okay, so I want to talk a little bit about the future now. And, to me, the future looks a lot like what was predicted in the past. If you look at the paper from Ivan Sutherland and actually put the real words in, not substitute Latin for copyright purposes, you would see that what he described actually became kind of the underlying ideas behind movies and books such as Ready Player One and a lot of people's vision about the future. Okay, so when I think about that future for XR, as was mentioned, I think by Jeff Burke earlier on, I think there are a lot of disciplines that come into play to make this happen. Clearly, there's the collaboration aspect of it and all the machinations of you know, getting images to people and doing millisecond level synchronization, et cetera. But improvements in immersion and the impact of AI and ML in this space is super important, I think, as well. Okay, so I'm first going to talk a little bit about collaboration. And again, mostly from a commercial environment. So there'll be lots of pretty pictures here, and apologies for that. But, you know, Microsoft is a big corporation, but they have a guy named Alex Kipman there who's driving their Windows mixed reality efforts. And they have some pretty distinct views about what collaboration should look like. So, for example, if you've ever seen this video, the people involved are able, it's very multimodal. People are using HoloLenses, they're using Vives, they're using holoportation booths, et cetera, and yet they're able to meet in a common environment with some representation or avatar in that environment and be very expressive and interactive with each other. There are a whole bunch of other companies, and I should say, there's a guy named Martin Ethned that used to be at IKEA. I think he's elsewhere now, but he did a survey of all the collaborative VR experiences and was interviewed on that. And I think at one point he had counted more than 60 different experiences available in the marketplace. And these are just a few of those. So there's a company in Helsinki, company I think is called Fake, but the collaborative environment is called Glue. It's very kind of representational, but the experiences are very, very good, and they allow things like import of CAD models and things of that nature. But it's quite good, and I actually just did a demo of their new version yesterday and was really impressed. There's a company called Virtualytics, and they use a collaborative VR environment for exploring data science or data activities, and really, really effective because you can see what other people are looking at and pointing at. You can manipulate objects and change some of the parameters around the data science views as well. So pretty cool stuff. We're working pretty closely with a company called Pixo VR, and they're based in the Midwest here, and it is an interactive and collaborative environment. It does enable people to join via desktop, but the better experiences are clearly in immersive tech. And these guys are all about safety training. So OSHA safety training in the US is a big deal, as it turns out. So they have a solution for that. And whoops, I went the wrong way. Sorry about that. And then some of you might know this company. It's Engage. They're based out of Dublin, I believe, or Dublin area in Ireland. And they're useful in a lot of different ways, but they're kind of targeted at education marketplace. And we've actually had some meetings at HP inside Engage, staff meetings and such, and it works quite well, actually. So on the topic of education, while we're there then, I wanted to talk about something that's going on locally, and I think, Francisco, you alluded to this earlier, maybe, which is this. So at CSU, there's a person named Dr. Todd Clapp and his team, which is Chad and Jordan and a few other folks at Colorado State University. And they put this immersive lab together, which is pretty impressive by scale alone, if nothing else. But the idea is that to teach gross anatomy, they have 100 systems arranged in 25 pods of 4 systems. They happen to be HP systems with pretty high-end graphics cards. They're mounted in the ceiling, and the headsets dangle. Students get into groups of 4, and they explore anatomy together. It's kind of an interesting workflow. They have one set of controllers in the situation. That's partly because of the workflow, but also partly because of the mechanics of having 100 different Bluetooth devices in a given room is not a trivial thing, as it turns out. but there's a leader in the experience, and they lead the team of 4 through an anatomy course or understanding of the day. There is voice control as well, so Cortana, I believe, comes into play here. And Todd and his team implemented this. They've actually spun a company off now, just FYI. It's called Prospectus, and the software, for reasons unknown to me, is called Banana Vision VR. But they're now productizing this, and they're taking it to other domains as well. So School of Mines down the road here does crystal analysis and mineral analysis, and is using the software. So this is great. Nobody in this picture is wearing a mask, right? So this was pre-COVID. This is post-COVID, clearly not as high utilization. And, this is a big problem. The course has continued, but the lab is not usable anymore. So Todd and his team took a sidestep and said, well, what can we do? And what they decided to do was take the headsets they had in that room, pair them up with a bunch of HP laptops that had high-end graphics in them. So these happen to be gaming laptops in this case, and actually ship them out to end students around the US. And there were 10 teaching assistants and 3 faculty involved in number 1, getting them shipped out, but number 2, and then teaching the course when this had happened. And so how did it go? Well, let's take a look at some images first. So this is a picture from Banana Vision, looking at obviously anatomical constructs here, both kind of 3D or polygonally oriented, as well as MRI scans and things of that nature. And you can see that the avatars are basically helmets, and if you're lucky, you have a helmet with a name. And the lead in this case would be Dr. Clapp, and he's pointing at structures, and the students are hopefully looking and paying attention to what he's saying. So pretty effective. So the summary, the takeaways that I got from Dr. Clapp were these, that the spatial relationships especially did very well in this kind of environment. So spatial relationships and scale of organs, for example, was a lot easier to understand here than it would be in a 2D environment. So if you just had 2D screens, obviously cadavers are probably even better, but a little less tasteful in some situations. The third bullet down is kind of interesting to me, is that the face-to-face and distance examination scores were pretty much equivalent. So things didn't suffer despite the fact that everybody was distributed around the country here. And about 2/3 of the students would enroll in a fully VR class again, and engagement was comparable. The 2/3 is, as a person in the industry, is a bit troubling for me. I'd like to see that closer to 80 or 90%. And I think I understand why that might be in some cases, but in the industry is generally working to make that better, to be honest. Okay, so that's that. So talked about collaboration, a little bit about education. Now, the 2 bottom aspects here, I think, again, play supporting roles and very important ones. And I was going to talk first about immersion a little bit. And, generally, lots of definitions of immersion. But if you think about just the physical level for a human, things like the acuity, the optical aspects, so getting data to the brain via the eyes, is a very interesting area. And the industry's been focusing very heavily on making the visual acuity better, optics better, field of view higher, color gamut broader, et cetera, et cetera. So a lot of effort in this space. Some in the oral area as well, AU, some in olfactory and so forth. But most of the impact's really been in the visual area, to be honest, so far. Now, if we expand out and not just what can we send to the human, but what can we glean from the human, there's a whole bunch of things that are being explored in the industry right now, and in academia, of course. So things like cognitive load can be measured if you have the right equipment on your headset. You can determine expression of the person, emotion, and some basic health parameters as well. And things get very interesting when you think about a feedback loop where you're able to inform the experience the person has with the senses on the right with derivations of the takeaways on the left. So I'll be talking about that in a little bit. Okay, so here's the part that starts to sound like a product introduction or something, and apologies for that again. But we do have a headset coming out here in about a month that's called the Reverb Gen 2 Omnicept Edition. Not a really succinct name, unfortunately, but it's got a really, really good visual experience. So it's got high resolution panels, 2160 squared per eye. It's got very advanced optics from our friends at Valve up in the Northwest. It's got optimized spatial audio for location 3 space, array microphones. But then the last 4 things are maybe the most interesting, which are, it has eye tracking, like some previous headsets, such as the Vive Pro Eye, but it's also got pupillometry. It's got heart rate and heart rate variability measured, and it actually has a lower face cam as well. And I'll briefly hold up an example here. So that's what it's going to look like. It's got 4 camera tracking too, so it does a better job tracking the controllers than previous headsets. So what can you do with all that? Okay, well, first off, I guess it's part of an overall ecosystem. So there's the headset on the left. We've created an SDK for developers, which gives you access to both the low-level functions, such as the camera, et cetera, but also some inferences which are derived via machine learning. And I'll talk a bit more about those in a second here. And then we've also been reaching out to industry partners on the right there. So ISV plans to work with people like PixoVR, which I mentioned before, for training and so forth. Okay, so I won't dwell into this because this is fairly marketing oriented, but one of the things we do infer from the basic inputs I mentioned is cognitive load, kind of a linear scale thereof. And obviously, if you do a good job of this, it can be used to inform experiences such as training or education. You can imagine, for example, if you're teaching somebody how to do a complex task, you can keep an eye on how cognitively loaded they are. There tends to be a Goldilocks zone for that. So, in one end, they're not paying attention. The other end, they're overloaded. And kind of in the middle, in the Goldilocks zone, is where they're getting it and understanding and making progress and learning. So both in education and outright training scenarios, we think this is going to have a lot of utility. In addition, and apologies for the avatar there, there is a camera, and we have some other sensors we're looking at that we're hoping will help drive facial expressions in remote avatars. Okay, and that's probably coming a little later this year. The cognitive load should be available in about a month or so. Okay. Just to give you an idea how this is all done, it's pretty obvious, but in the headset, we have the sensors, we capture the physiological signals, we run them through a machine learning model, which is running on the local PC. And this is a tethered headset in this case, by the way. And then we extract the inferences. Okay, so how do we create that machine? Well, turns out we've been testing a huge, broad population of people around the world and with known annotated experiences, and using that to train the machine learning cluster using a cloud-based solution. That gets downloaded into the PC when you run, and it's a pretty succinct model by the time we're done. So I can easily run on a local PC. Okay, so that's the overall process. COVID has definitely impacted us in terms of our ability to gather data for not just cognitive load, but some of the future inferences we want to have as well. Okay. So, so back to Todd's classroom. Clearly, in my mind anyway, it seems like cognitive load, knowing that either on an individual basis, or if you want to maintain more privacy, maybe as an anonymous basis or a group basis, that could play into understanding how well the class is getting what you're teaching. One wonders about expression now. So in this situation, it's the model in the middle of this experience, which is really the interesting thing. It's not clear that you need to see what other people, what their facial expressions are. But if you think about other modalities such as architectural design, for example, where you're showing something to somebody and you want to gauge if they like it or not, for example, in case of a building, you can imagine having more expressive avatars would be pretty useful. Okay. So I think most of you are familiar with Siren. This was a digital human that was demonstrated by Epic and others in GDC in 2018. And it was really groundbreaking at the time, I think. The quality not only of the rendering, but also in the fidelity of the captured facial expressions was quite excellent. But to do that, you needed this pretty expensive and expansive rig on the right-hand side that the lady was wearing. What we're trying to do with our latest headset is to try and collapse that capability into a traditional VR headset, and a pretty good one, we think, and allow you to get that same kind of expression fidelity from the headset and drive a remote avatar. And I should also note that while, Siren on the left here is pretty impressive as a digital human, probably still has one foot in the uncanny valley, I'm going to say. But if you take a look at what Epic has just introduced with the MetaHumans, pretty impressive stuff. Probably still identifiable as digitally generated or non-human, but getting really, really good. So, in the next, I would say, 2 to 5 years or so, we expect to see some pretty amazing collaborative experiences with lifelike avatars that are very, very expressive. And I think that will benefit a lot of the collaborative opportunities we mentioned earlier. So I think that's my time. And thank you very much for having me, Francisco. And I guess we'll take questions a little bit later.
Thank you, Paul. And no need to apologize for the commercial aspect of it. I mean, by design, we wanted to have industry people. We did try to bring someone from Microsoft Research, but it did not happen as well. But we're glad to have at least one. So,
and the reason that didn't work, by the way, is he's actually retired now, by the way. Andy just retired. So.
Oh, he retired?
Yeah, sorry.
Maybe he can tell me more stuff now.
Okay, yeah.
So thank you, Paul, and send me 2 of those headsets, and I'll forgive anything. So thank you for that. And the next speaker is Greg White from Cable Labs. So take it away, and then we'll go into the Q&A session.
All right, let me share screen here. Okay, hopefully you can see that.
Yes.
All right. So I'm a little bit of an outsider here in this group. I don't actually do any work directly relating to virtual reality or collaborative experiences. I'm a networking guy, and I've been working developing network technologies for about 20 years. Mainly looking at broadband, internet access networks at Cable Labs. So Cable Labs is a nonprofit consortium. We develop technology for the cable industry. So the cable modem access network technology is really our claim to fame, DOCSIS. And but we work with network operators all around the world who fund our research and development activities, and we work with a lot of manufacturers and vendor companies to get them the new technologies realized. This talk will be about some of the aspects of networking that you need to consider when developing collaborative environments and collaborative experiences, and in particular, some of the new technologies that are being developed that will facilitate that in the near future. So go into the slides here. We talk about network requirements for these collaborative experiences, in particular VR. It all depends on where you're talking about in the network and where the different components are, right? The end user, for user-to-user collaboration, you need low latency, right? You need latencies that are kind of on the scale of 50 to 100 milliseconds to have a good collaborative experience. But then when you get down into the actual components of the system and how that's collaboration is enabled, talk about state synchronization. There's been a lot of discussion of that in some of the previous presentations. So here you're talking about from one renderer to another, how do you keep the state aligned in the virtual environment? And here, again, the latency requirements come into play. Similarly, 50 to 100 milliseconds is kind of the realm of latency performance that's needed. Obviously, lower is better, and there's no real hard line in terms of what works and what doesn't, but things degrade as latency increases. But the throughput requirements for state synchronization are relatively low, generally less than about a megabit per second in terms of the data that's sent between renderers to enable synchronization. And then the third piece, talk about remote rendering, where the rendering is done separate from the display, and in order to take advantage of maybe cloud computer, edge compute functionality, offload some of that processing from the user and from the headset. Here, the data rates are much higher, obviously, in the range of over 10 megabits per second, up to hundreds of megabits per second. And the latency requirements are much more stringent on the network side. So on the order of low single-digit milliseconds for a round trip between the renderer and the display, in order to ensure that as you add in the rendering time and encode time and things like that, that you add up to a motion to photon latency that's on the order of 15 to 20 milliseconds at most. So the network aspects of this, what adds up to create the latency between the different elements of the system? So I've broken it down here into four main components. One obviously is the geography. Where are these entities that we're networking together, and what connects those entities? What is the network topology between them? And here latency is driven largely by the speed of light and speed of light in glass, 2 times 10 to the 8th meters per second. But also the topology comes into play, and so it's not just the geographical distance between the entities, but also the network topology piece. So there's path stretch that comes into play there. And then we're also talking about round trip. So to multiply that that distance by 2, and you end up with order of magnitude 60 kilometers per millisecond of latency between network elements. Next piece, congestion and buffering. This is a huge contributor to latency and latency variation in networking today. And I'll talk a bit more about that in some detail on the next slides coming up. And a couple of approaches have been attempted in the past, or some approaches have been attempted in the past. Others are emerging as solutions to this, or ways to mitigate the effects of congestion and buffering in networks. And then the last two components, media access and physical layer delays. These are really technology dependent, and are prevalent really in LAN technologies as well as access network technologies, where you've got things like multi-user LAN technologies like Wi-Fi, where you've got contention for access to the channel, things like that. And then physical layer delays, which can be fairly short in terms of getting bits onto the wire or onto the air, but some networking technologies have bigger issues there. Like, for example, DSL networks can turn on interleaving, which can add 10 or 20 milliseconds of latency to the path. And then the paths are not generally symmetric. So even within access network technologies, you can see significant differences in latency one direction versus the other. And then in routed paths across the internet, it's actually fairly uncommon for the traffic in one direction to take the same path as the return traffic takes. And so asymmetry is pretty common, but it's usually irrelevant. We're talking about collaboration, right? It's a round trip. Time is what matters. Right, on this path stretch piece, so this 1.7x, I had that on the previous slide as well. It's a good rule of thumb in terms of how to estimate latency for versus geographical distance. The scatter plot here is from a data set published by CADA at the University of San Diego, where they have thousands of probe devices that are scattered around the world that they do measurements from those probe devices. And there's a plot of median round trip time versus geographical distance. The black line is what you'd predict based on the speed of light in glass. 1.7 is this stretch factor, which accounts for the fact that networks aren't line of sight, and packets take a path through the network that it does not go directly from the user to the server. All right. So latency variation. This is actually one of the biggest issues, I think, in developing interactive real-time systems on the internet. And not only is there fixed latencies due to geographical distance and topology, but there's latency variation over time. And this manifests itself in across different time scales, as networks change and evolve, and new interconnections are made in the internet. Things change, but they also change on much finer grain time scale. So the graph on this slide shows measurements that we've taken in our labs around network performance in typical and congested environments, where you see the minimum latency could be on the order of less than 10 milliseconds, but you see these quite a bit of variation on the order of tens to hundreds of milliseconds, with spikes going up to well over 100 milliseconds of latency. Clearly, any collaborative experience that's lasting for multiple seconds or multiple minutes is going to have to take into account these kinds of latency variations and come up with ways to deal with them. So what causes these short-term variations in latency? And the root cause of it is congestion. And it's not congestion in the sense of that users are trying to push more traffic through the network than it can support, or they're trying to do more in the way of video streaming or downloads than the network is able to support. It's really the way networking protocols that run on end systems make use of the network. And so the vast majority of traffic that flows across the internet today is congestion controlled traffic. So it essentially is trying to sense the available capacity of the network and make use of that available capacity. And in general, you've got multiple applications or multiple sessions that are sharing a network and are competing for the available capacity. And generally, with the congestion control algorithms that are in use today, competing relatively fairly for access to that capacity and getting roughly equivalent throughput across a bottleneck link. But the way they do that is typically is they ramp up their sending rate until they see a congestion signal from the network. And ordinarily, that congestion signal is packet loss. And so as the sender ramps up the sending rate, it at some point is exceeding the available capacity of the path. It is sending traffic faster than the network can support, and that traffic backs up in buffers in the network and generally at the bottleneck link along that path. The buffer builds up. That's causing latency now for all the traffic that's sharing that link. And then eventually that buffer fills up till it's full, a packet gets dropped, and that gap in the packet sequence is detected by the receiver. The receiver sends feedback to the sender. The sender adjusts its sending rate, or in the case of TCP, its congestion window, in order to reduce its load on the network. And so this is all happening over time as sessions come and go. They rapidly ramp up to try to sense the available capacity, causing this buffering to occur. And then during the file transfer or during the session, they're continually probing for capacity, and again, causing packet loss, causing latency for all of the applications that are sharing that path. And so, so thinking back to that previous graph on this slide, this is a series of TCP file transfers that are happening during this 2-minute test. You see, those large spikes are caused by a TCP session starting up and doing its initial probing for capacity, and then the variation in between those large spikes is its continual probe for available capacity and the latency that causes. So what do you? How do you deal with this? How do you develop applications that can survive in these network environments where even the baseline latency might be not ideal, but then when you add in that latency variation, it becomes extremely difficult to keep state synchronized or to keep the display lined up with the head motion. So 2 aspects here. One is on the application side itself, you're building the application to handle that delay variation, and this is a long history of different approaches there. Not only in online gaming and VR type applications, but also other isochronous applications like voice over IP, where delay variation has to be dealt with. So some of the approaches that have been used there are rollback approaches, where you handle the state updates and inputs as they arrive, and you project state forward to the current time, and as new updates arrive, perhaps delayed by the latency variation, you rewind the clock till you can align the state representation internally with the new state information received, and then fast forward the clock again to current time to handle those late arriving state updates. And then de-jitter buffers, and for applications that are a little bit more tolerant of fixed delay, a de-jitter buffer basically converts latency variation into a fixed delay and packet loss. So packet delays that exceed what the de-jitter buffer can handle end up being handled as packet loss. So that's in the application itself, but then the other aspect is, what can you do with the network in order to reduce delay variation and minimize the need for long de-jitter buffers, or for these rollback approaches, which can cause glitches in the experience. And here there are a couple of approaches. One I label as traditional quality of service approaches. So anyone who's been around networking for a while would be familiar with some of the approaches that have been tried in the past in order to improve performance for certain applications. I'll talk a little bit about that. And then I'll talk more about some emerging technology called L4S and NQB, which are networking technologies and application layer technologies that are intended to significantly improve latency performance for real-time applications. All right, the traditional QoS piece, or quality of service piece, in general, equates to prioritization. There have been attempts in the past at things that are referred to as parameterized QoS, where an application defines its behavior in terms of bandwidth and packet size and things like that, and try to reserve access for itself, for its traffic on the network. Those have generally been extremely complex in order to implement, and have not been very successful. But prioritization has been fairly successful in certain environments, particularly enterprise network environments, as well as between large ISPs for handling certain types of traffic. The idea here is that you identify the important traffic or the latency sensitive traffic, and you give that traffic higher bandwidth priority along the routers and switches in the path. Some of the issues that come into play when trying to implement these traditional prioritization schemes are, one is, how do you identify the traffic? What are the APIs that an application needs to use to communicate with the network in order to identify the traffic and get the right priority? And then going along with that is admission control and policing. So how do you ensure that you're not oversubscribing the network with more high priority traffic than you can support? Because if everything indicates that it's high priority, then nothing's high priority, right? So controlling access to that high priority queue or set of queues is an important piece, and policing the use of it, making sure that the right traffic is getting access and the wrong traffic isn't. And beyond that, you get into some kind of higher layer issues like across domains, across networks. How do you get quality of service end to end when it's not just a single network operator that you're dealing with, but you're dealing with potentially multiple networks, multiple business entities that have their own goals and policies around network priority and quality of service. The next one would be a regulatory side. So for broadband access in a lot of jurisdictions in the world, there are, if not enforced legal ramifications around prioritization of traffic. But in other cases, there may be guidelines or other rules of engagement around making fast lanes for certain types of traffic. Paid prioritization is illegal in some cases. And then kind of more generally, these mechanisms rely on making value judgments, right? You're making, the words important and latency sensitive towards the top of the slide, I put in quotes because the importance is subjective, right? As is latency sensitivity. Every application degrades as latency increases, weighing degradation of an application versus degradation of another application is inherently a value judgment. And finally, prioritization enforces this kind of zero-sum game. It's you can give prioritization to some traffic at the expense of other traffic, and it relies on there being other traffic that that can take the hit and be placed at a lower priority. Recognizing the issues that come along with prioritization, there's some emerging technology that is going through the standardization process in the IETF. Really two kind of components to it, one called L4S, the other one called NQB. We've got the names of the key IETF drafts under that first top level bullet there. If you're interested in more detail on any of these, you could Google those drafts and read up on it. But in essence, L4S stands for low latency, low loss, scalable transport. It is a new incrementally deployable congestion control architecture. So thinking back to the description I gave earlier about congestion control being the source of a lot of the latency variation, L4S solves that, right? It allows a network to give high fidelity congestion signals to applications, and then they can respond to that and prevent latency and loss, fully utilize the network capacity without causing all the delay and loss. So ideal for remote rendered VR applications, things like that are high bandwidth, want to be able to fully utilize the network. The second piece, NQB, stands for non-queue building. It recognizes that, yes, there are a lot of applications. The majority of applications today are trying to sense the capacity of the network and fully utilize it. But there are also a whole lot of applications that don't do that, that are fairly sparse sending applications. They're not probing for capacity, and in general, they're not contributing to latency by building up queues in the network. So here are some examples would be the state synchronization between collaborative virtual environments, as well as real-time communication. We won't have time to go into a lot of detail on how this works. You can certainly look at the drafts I pointed to on the previous slide, but really three components in the network element that enable both of these functionalities. The core of it is two queues. So one queue for what we call low latency traffic that is non-queue building or supports L4S, and the other queue for essentially everything else. We call it the classic queue. It has a deep buffer. It allows the existing congestion control algorithms like TCP that TCP uses to get great throughput. It's not high priority and low priority. It's not a good queue and a bad queue. They're both great queues, just optimized for those two different types of traffic. And then coupled active queue management allows consistent congestion signals between both queues so that fairness can be achieved across traffic going in both of those queues. And the last piece is queue protection, which is monitoring all of the traffic that's going into the low latency queue and validating that it is not contributing to latency itself. And if it is contributing to latency, then redirecting that traffic to the classic queue. So a kind of a trust but verify approach there. Just to wrap up, your application support for these technologies depends on if it's a low data rate stream using that NQB functionality. It's marking traffic in the IP header with a diff code point. For high data rate streams, a little bit more complicated. The detailed requirements are in IETF draft. And the kind of high level advantages of this approach. It's up to the application to decide which queue works best for it, the low latency queue or the classic queue. There's really no benefit for an application in selecting the wrong queue and in trying to get into the low latency queue when it really would do better in the classic queue. But then on top of that, the policing is based on objective behavior. It's not based on importance or subjective latency sensitivity. It's really based on, are you causing latency or are you not causing latency? And as long as you're well behaved, you can stay in a low latency queue. And then last slide. So this technology we've adopted in an evolution of the cable modem technology, we call it low latency DOCSIS. It's a software upgrade to existing DOCSIS 3.1 equipment, so we'll start getting deployed in access networks later this year and into next year. And other network technologies such as 5G have been discussing how to adopt this functionality as well. I think that's it for me, and I'll hand it back to Francisco.
Thank you so much. It was a great presentation. Thank you to the three panelists. Again, I want to thank my co-organizers, and I forgot to thank the external reviewers we have for the papers. So thank you external reviewers. I did post the site for the conference. We'll have papers there. They'll also be available on the IEEE proceedings. If you haven't registered, it's a great conference. I think you can still register, I'm not sure. And the videos of this workshop will be available, I believe, in the IEEE website at some point a few weeks from now. So thank you so much. Thanks, everybody. Now we're going to go into a Q&A type of panel session. I invite any of my co-organizers are here to participate, as well as all the attendees. Whether you're watching this via Zoom and you want to post the question there or just ask the question, or if you want to do it in Discord, please do so. I would also invite, only if you want to, of course, to people to turn on their cameras so we can see. This will be like the most interactive, collaborative session part of this conference. If you want, you don't have to, but if you have a camera and you can turn it on, it will be greatly appreciated. Um, the So one thing that I wanted to say was that this was a great, the design of this workshop was to bring people from different backgrounds, right? And I think it seems that we have been able to accomplish that. And I think it's going to lead to great questions. One of the things that I asked the attendees and anybody else here to think further as well is that what are the things that researchers need? And I want to give you some examples. We developed something similar to the spatial markers for Microsoft. We haven't released it because it's not complete, but one of the reasons we did it is not that because there was nothing out there. It's because we couldn't get access to the source code and we wanted to make changes. So if you think about software that could be used, this would be a great thing for you to add on survey 1 or survey 2, which I do appreciate if you can do it. We have only 5 responses. You can do it tomorrow whenever you want. And we have great prices. So right now, the people that have to fill this in seems that have great opportunities because the rough is going to be pretty much a one-to-one mapping if we are continue like this. So think about those things. Think about as a researcher, and this can help industry as well because we can use those tools and they can use it later. But what are we missing that will make our research better? And again, this is one of the reasons that we're going to go back to NS7 says, look, this is what the community needs, and we can use, get this infrastructure so that they can use it and things like that. And this could be used by anywhere, not just people in the US, even though the proposal is US centric. With this, I'll open the session and the panelists can ask themselves questions too if they want.
Good.
Of course, it was implied, but I wanted to be explicit about it. And Faisal, you can help me with the Discord if there's any questions. So the one thing that I wanted to ask Anthony, and then I'll lead to the rest of the panel because it's related, is when we think about manipulation of objects, virtual objects, right? Let's think about that you're using augmented reality headsets, you're in different places. Now, latency becomes a real problem. And of course, games have been able to do this. And for example, we have used the Photon engine. Again, we don't have access to a source code, which if we're gonna make changes is a problem. But what do you see are the biggest challenges to make this synchronous? Because this is the biggest problem, synchronous remote collaborative environments that we're facing from the point of view of AR, VR, and then of course all networking and the rest of the panelists can answer anything on that. So I will start on that, and also feel free to say anything else that may be relevant to this or something else. So I'll start with Anthony, and then we'll go to the rest.
Sure. So this is something that we've published a couple of papers on recently. The thing about synchronization is that the thing about synchronization is synchronization to what? The most important thing for the VR is that each site see something plausible. So they all tend to run their physics engines, for example, and therefore keep collisions inconsistent. So the way I talk about it is that you're not trying to make them synchronize them. You're trying to sort of make them non-divergent, at least, and they're converging slowly, or at least it's not a strict constraint in the way that distributed systems people talk about it. Because if you just start doing it's synchronous, therefore I'm going to send a packet, it has to start getting all these round trip confirmations and so on, you end up with very high latencies. So you tend to send packets, they get lost, you send packets and they get out of order. You don't care, you try and synchronize things slowly because the actual implications of that are sort of need to be understood at a system level. So Francesco probably asked this because it's a question without a really good answer to start off with. If you're just going to pick up an object, one object and move it, that's simple, right? I mean, the only thing that tends to go wrong in several social VR systems that are out there is they're sending this unreliably because it's fast, but they forget that there's a tail end problem on their packet sequence, which is common in many sort of older VR systems, that I pick up an object and I move it and it's got dynamics on it to make it, but you forget to send the very reliable packet at the end that says I've stopped. And you could still, I tell my students to go and find that in VR systems, social VR systems that are out there, distributed systems, that the latency makes some assumptions, but there is state change in streaming, which is actually really important, and as it isn't dealt very well with certain protocols that are out there, and why we end up rolling our own every so often. So there, and yeah, we use Photon, we use all these other things. That's why we built our own, because so we know exactly what's going on. And the paper that we're presenting later this week basically is an argument against using dead reckoning, and pointing out that in certain situations, dead reckoning is going to make your life worse over local area networks, and you basically shouldn't do it, right? It's going to and also it's also very variable. So so what do I suggest? I mean, more tools is good, but also looking at exactly what's happening, and looking and treating it as a sort of experimental platform where you can record data and do forensics on it. And again, that's some of the stuff that we're putting in these tools that we've just released is observation of what actually went on the network. So you can understand why the object jumps at the end or did this at the end, because actually network conditions changing on different timescales, as Greg said, is very true, and it'll bite you at exactly the wrong time, right? Especially if you're doing physics simulations, right? I mean, it'll switch and you'll be making a prediction, and unbeknownst to you, the network conditions will have changed underneath you whilst it's at, well, partly it's just awareness raising that these things go on. and it's a bit of a what do you call it, dangerous world out there in networking.
I had a question, if I might.
Yes.
Real quickly, Greg, I think I know the answer to this, but I'll just ask it kind of rhetorically, I guess. Is there any impact to some of the new network physical layers or whatever that are emerging, such as Starlink, kind of low Earth orbit-y, satellite distribution? Does that have any impact on any of that, or are the problems pretty much still the same?
So in general, the problems with congestion and congestion control are the same regardless of link technology. It's kind of built into the TCP congestion control stack that runs on the end systems, and it's an evolving space, right? There are back in the day, the Reno algorithm was the main congestion control algorithm that was used, and then 5 years ago or so, Cubic became the main algorithm, and now Google has a newer algorithm called BBR, which is currently the most widely deployed. So from that perspective, yeah, I mean that the congestion and latency variation caused by congestion is going to be materially the same across different network technologies. What how the different technologies handle that, whether it's just a simple FIFO buffer at the bottleneck, or whether it's something more sophisticated with some active queue management techniques, or this newer technology called L4S, that will affect things quite a bit. The other thing around things like the low Earth orbit satellite systems that are starting to get deployed, that relates to latency, is for short distance communication, right? So the majority of the traffic that traverses access networks is not going very far. It's going to a CDN node in the metro area of the user. That traffic is going to be have higher latency with low Earth orbit satellites, right? Because it's got a much farther path to traverse. But longer distance communication may end up being lower latency over low Earth orbit constellations when they get to the point of having inter-satellite links, because the speed of light in air or speed of light in vacuum is 50% faster than it is in glass, and those paths are much closer to line of sight, right? If you go, 1 or 2 satellite hops versus going through a fiber path that follows rights of way along highways and things like that. So, yeah, I think there's a future ahead where global communication, global scale communication could be lower latency over satellite.
Cool, thank you.
Thank you. I want to read a question posted by Nico Feld. And it's open to anybody who wants to answer from the panel. What do you think about WebXR as a solution to problems like accessibility for users, content delivery, and limiting app stores? Or I don't know if he's limiting or eliminating app stores. I'm not sure. Nico, feel free to expand the question if you like. Limiting, yeah. So I'll read it one more time. What do you think about WebXR as a solution to problems like accessibility for users, context delivery, or limiting app stores? And I would say that I do think that WebXR is having some problems, if I'm not mistaken, in terms of the future. But something like WebXR could also, be part of the question. So go ahead, and anybody on the panel that would like to take this.
I can talk a little bit about WebXR. There's an interesting intention, but unfortunately, it's going to hit some technical hurdles. So if it sits between, it is a very good way of delivering content to people because it sits in a web security model, and therefore you just deliver at runtime. But that is, of course, its downfall as well, because it hits these caching problems. 2 main problems. One is the size of the thing you can deliver, caching, and also the caching of that. And the second one is the web security model, and the fact that it's page-based security is unfortunately a bit of a limitation. If you start digging into it, it's a bit of a limitation in how you might build a really large collaborative system, especially if you've got lots of peers in it. So yeah, that's my main one set of worries. So the main plus is you can get stuff to people. The main minus is that obviously that comes with limitations. The web security one is actually a really deep problem, which has other implications for how things run on the internet, and is being tackled by the W3C, but it's a thorny problem because it's down to this trustable code thing, right? I mean, it's just fundamentally it's not something that anybody. It's a distributed systems problem. It's not just a Google hasn't got enough engineers in Chrome to build it. It's a fundamental problem with distributed systems. There's a second set of problems which I think speaks more to the content creation, which I think delivering things to WebXR is a mess. So I think content, the reason that game engines have won for the moment is because of the asset store. And they, as I said, when you build an engine, when you build this social system at the moment, you're building a runtime and a production pipeline for it at the same time, and that production pipeline is not there for the WebXR. And some of the most interesting things that Mozilla did last year, before the last conference, things like the hub and spoke and the ways that you build stuff for their system. And there needs to be, that's the challenge, is there needs to be a lot more of those sort of content development systems. because yeah, to bring stuff into that model. So yeah, so I think there's there are pros and cons. If you want to get into low-level systems design, unfortunately, you inherit so much from the browser context, it's difficult to get at the real issues, or at least at the interesting issues. So I'm afraid we're not working on it at the moment. Not that that's so we just don't feel that we can work on that at the moment, apart from some students build projects that deliver things to WebXR, but our experiments in collaborative systems are staying away from it at the moment.
Anyone else would like to answer this question, or we can move to the next one? Yeah, go ahead.
Francisco, I see a hand.
Okay, yes. And Argela?
Hello. Can you hear me?
Yeah. Just one second.
Yes.
Just a quick announcement for those of people that are in the IEEE VR conference tomorrow. The conference go to GMT +1, which I think is an hour later for me or something. But anyways, just to quick announcement on that. Go ahead, please. I apologize for interrupting you.
No problem. First of all, thank you very much for the interesting presentations. And to introduce myself, I'm working at an engineering institute as a PhD student, and at the moment on the research on asynchronous collaboration. But before, I was doing my master's thesis on synchronous collaboration, and there we tried to extend our VR engine by a synchronization module. And now I wanted to ask for your opinions on peer-to-peer topologies for immersive collaboration, because our thought was we are not in the gaming industry, but in engineering. We do not want to have a central cheat control or something. And also many companies in the industry who are working on CED data have confidential information which they don't want to share on servers. And yes, since we have so much expertise together, I would like to hear your opinions.
I could talk about that as well, unless somebody else wants to jump in. And so, yeah, so we just released a social VR system which has a server, and the reason for that is the internet's not symmetric. So you can plan to be peer-to-peer. On a LAN, fine, but not on the internet. Essentially. So the main thing that slowed us down releasing our system was we are using peer-to-peer audio using WebRTC, but obviously that, because you don't want to be relaying that, except of course you end up doing it anyway, right? So we've burning some Azure credits on the moment, running turn servers for people so that they can actually talk to each other. So yeah, so you're just caught between a rock and a hard place. Yes, you can be peer-to-peer, but that's the first thing you should test. If your network is not transparently peer-to-peer, then you'll end up with something like a relay server anyway. There are toolkits you can buy that will hide that fact from you if you want, but obviously that's an added layer of complexity. Yeah, so our server and our system is very dumb. It's basically a relay and will hold data persistently in case of transient connections. But yeah, in other situations where we have two clients we know that are on the same subnet, then of course we'd relay things peer-to-peer and then only correct if they went via the server and was seen to be had to be rectified. So yeah, there isn't a right solution. There's just lots of options, and that's one of the things that complicates this space. Yeah.
Paul or Greg, would you like to say anything about it?
I understand what Anthony just said, but yeah, and agree. There's clearly a need in industry though for something that is more private, let's say, and peer-to-peer would be great, but hard to achieve in reality unless you have a dedicated trunk between two companies, for example, or within a company. So tough problem, I think.
Greg?
Yeah, I similar thoughts, I guess. I mean, I think you try to establish peer-to-peer communication when you can, and but difficult to rely on that in across a broad range of network environments, firewalls, and things like that. And I think there's a potentially a role for edge compute or the more localized compute for providing rendezvous and relay capabilities that can avoid the need for having a single hub and spoke type of architecture. But yeah, direct peer-to-peer, I think it is challenging for sure.
So I had a question, Greg, on payload size and average latency latency or expected latency or something. There are ways to make an immersive experience more edge node based, where you're doing a lot of the rendering and you're just sending locally and you're sending positional information between, as opposed to having more of a video approach or something similar, as Jeff mentioned up front. Is there, I assume there's some kind of correlation with payload, amount of traffic, bandwidth, and latency in some of the more advanced systems you might be proposing. So for example, if I can cut my the data traffic way down, does that help in terms of end-to-end latency? I wonder.
Right. So in the L4S and NQB approach, the intent is that you can get low latency regardless of what your sender behavior is in terms of data rate. So it's a very simple proposition to implement if you have sparse traffic, if you're sending your state update information or audio packets for the voice channel. That's really straightforward. Your data rate there is very unlikely to be exceeding the capacity of the path between from one point to the other. But the L4S component really is intended for applications that are high data rate, like cloud rendered VR, cloud rendered games, that kind of thing, where you do want to be sending at 10, 20, 50, 100 megabits per second, ideally, in order to get the resolution, video resolution that you want. But you're unlikely to be guaranteed to have that much capacity between the renderer and the client. And you have to be able to adjust that codec rate in order to not overrun the available capacity on the path. And so that's where this very fine-grained and high-fidelity congestion feedback that the network provides comes into play. And as long as the sender has this feedback loop, it can respond to those congestion signals and kind of fly underneath the queuing delay threshold of the network. Yep, exactly. Adjust the codec rate down when it sees congestion, and have a way to ramp that back up as congestion diminishes. So yeah.
Okay.
At the end of the day, the goal is that all applications that want low latency can get low latency. They just have to play by the rules.
Okay, cool. Thank you.
So Faisa, you had a question. Go ahead.
Yes. So my question is from Dr. Esty. I wanted to know so about UBIQ's application, if I'm correct. What is the limitation, the number of people who can connect to UBIQ, and how many headsets can connect, and is there any limitation on the VR headset that connect to it?
Okay, yes, the Ubiquitous is being tested. So it uses WebRTC audio, so that maxes out at about 20 connections, as you can tell with pretty much any system that uses it, and that, you can get more, but we don't have any sort of scalability management yet in the system, because that's not our target. Our target's sort of small groups, like 3 to 10 people. And then the other part of the question was,
is it compatible with all?
Yes, the headset. Sorry, yes. Well, the examples include building for anything that Unity supports. So yeah, we've tested it. We do most of our testing on Quest, on the Oculus Quest. I have built it for the Valve Index because I've got one. I've built it for the Vaho XR1 as well, just because I've got one of those as well. Because my lab at UCL has slowly migrated into my study at home. So it works on that, but that's just because, you know, it's just one-click build. There are things it doesn't support. The Unity is on this sort of threshold of supporting OpenXR or not, and it's a mess. So we have actually stuck with a fairly old version of Unity because our demo doesn't work in Unity 2020 something or other, because they messed up something about driver support for some of the head-mounted displays. So you can turn on OpenXR, but then it doesn't work for Oculus or something like that. I forget what. I have postdocs that scratch their heads when they look at that. So we have stuck with Unity 2019 for the moment, because it's uniform for everything. It's not the latest versions of the drivers, but yeah, it pretty works. Yeah, if Unity works on it. We haven't tried it on anything really low power. I haven't tried it on a HoloLens, but there's no real reason why it shouldn't work. We can build for Android, and I don't think we've built it for iOS as well. No, we haven't built it for iOS. No, we haven't built it for iOS. We have done Macs. Yeah.
And also, sorry about it. And the engine that we are using in that is, you said, Photon engine for this one as well, or is it?
Nope. No. So so it's all our own networking.
Okay.
But partly so we can play with some of these novel reliability protocols. So we support different transports. It's hidden. You won't see it as a user trying it, but you'll see it in the code as we have played with some of these transports. We have our own networks, right? We have our own optical network to play with. So where we don't, you write direct, you can do very customized things. So yeah, so we we're
thank you very much.
Thank you. Do we have anyone else would like to ask a question? Like, do invite anybody, the keynotes, the organizers, anybody would like to ask a question? The attendees.
Yeah, so I'll ask a quick question. So Jeff touched on the machine learning aspect of it in the morning. So if you could comment on where things are and how do you think machine learning can play a role in reducing latency, that'd be great.
Interesting. So there is a there are examples of machine learning applied to networking already. One of them, and I'm going to forget the name, is a paper that Microsoft did a few years ago for Halo. So they're doing the network of that. So they do the simulation. So it's a really interesting idea. So that I'm not sure if it's used live in the game, but what they had is that they obviously have non-player characters. So you can train an agent to play the game. And they do that by looking at thousands of real users playing the game. And then they optimize agents that pretend to be players of the game. The thing about that is then if you look at a player behavior, you can tell if they're acting like a bot or not. Because really good players tend to have to, navigate like bots in order to get between the places accurately. So they learned behaviors. So they have a paper, and the name may come to me, and I'll type it in the chat later. It's a really interesting paper where they actually showed that they could network the game together by sending packets every second or few seconds, because they're basically saying, it's like bot number 1, it's like bot number 10,007. And so all they send is send you some coding of what they were playing like, and then it would run that simulation for a few seconds. So that's certainly one thing to do. And then if you get into there's so that's sort of a straightforward compression within a constrained domain, and then looking at can you then optimize for that. Well, obviously it has to be a constrained domain. Human animation may be a fairly constrained domain. I don't think anybody's shown that yet, but it's one way of compressing animation. Yeah, obviously there's bits happening in video. You might have seen a video, I forget, it's from Microsoft in the last few days, of compressing, I forgot who it was from, but they were compressing Skype-like video by sending a photograph and then animating it and claiming they were saving masses of bandwidth. So you can imagine doing that for video or pictures or so on. And again, but that's sort of, it needs tied into a context. So my first look at that was really cool, but then it's sort of, if it's just a head talking, it's not a very interesting case. And it was definitely uncanny. That's what everybody said about it. It's already uncanny. So you can just treat it as a compression problem, and then it's just a case of what's the domain you're compressing over, and you can use machine learning for that. But bear in mind that because it's humans, you can, the result may have, the errors from a compressor will possibly catch the eye of a human looking at it.
Yeah,
and that might be related to what Paul's doing with the HP stuff with the tracking. I mean, it's in the margins. It's like it has to be high quality, because otherwise humans are
very good at looking at humans. Yeah,
very good at looking at humans.
Yeah. And understanding
something about them.
Yeah, what about those humans? And I think NVIDIA is doing work on the compression based on determining tracking points on the face and then animating a video on the other end as well. It's I think 3 orders of magnitude compression or something like that. But yeah, what does it look like? Question mark. It's part of their Maxine toolkit, I believe. And so.
On the networking, congestion side of things, there are algorithms that have been attempted to try to predict capacity in the future, right? So you can adjust your rate controller for the compression algorithm in order to ensure that you maintain low latency. Those, at least the most successful ones of those that I've seen recently, it's all requires online learning, right? So it's not sufficient to train a model based on hours and hours of network performance recordings and then run that algorithm. You really need to train live based on attempting to predict available capacity and then comparing what the actual available capacity to what you predicted.
Yeah, on the facial animation by animating a remote picture effectively, there was a pretty good paper at SIGGRAPH, I think late 80s, something maybe early 90s, on video conferencing with that kind of a technique, and they would animate only certain parts of the face, and in the highest data compression areas where they basically animated the mouth but nothing else, you had the feeling you were talking with a killer on the other side. Eyes would never move and looked intently at you. So it was a pretty good paper though, because they varied kind of the expressivity and traded that off versus the bandwidth and how good it looked, judged by an impartial panel. So something to take a look at.
Thank you. And hopefully there'll be a little time for extra question. We still have a little bit of time. I'm going to go ahead and ask this question to the three of you. And you can answer from your point of view, whether it's networking, AR, VR research, or from the industry point of view. But what do you think is missing, or what kind of tools would you need to, if you're a researcher, to enable your research in this area of collaborative environment? And if your industry, what do you think that you will need from research or researchers to improve your current state in terms of collaborative environments? And I gave an example earlier, and I think the examples that Anthony, he's been releasing things because he really needs to do, be able to have access to the code. I think this is a great example, right? Like for us, at least for me as a researcher, not only to create new things, but sometimes if I don't have access to modify things, it's hard for me to do the research. So I'll just leave it open and also share anything else that you want. I don't know if you want to start, Anthony, and then we'll go to Paul and Greg.
So I do need new tools, but testing networks, testing sort of strategies for networking, simulation. I need simulation tools. Without, one of the things we find difficult is testing at scale. Because you can run things on network simulators, you never learn quite what you want. But another thing I'd say, based on some other activities I'm involved in, is there is actually quite a lot of experience out there. So I would, not for the companies represented here, but there are people providing sort of social VR systems, and I'd love to see data. So if there was a way of doing that, that we could see what the people are doing, find the usability problems that are emerging from the network, because my conviction for a long time has been that network problems manifest as social problems eventually. They are somebody's on a lower latency link, well, obviously they're going to get shot in most first-person shooters. But what does that mean if they're trying to have a negotiation for salary increase, right? So I think sort of getting that data and getting and then doing these sort of whole stack experiments on what implications this has of the social situation is working with people that have that data, I think is a big opportunity. Because I think obviously we're expecting to use these tools more and more, and therefore they're going to become increasingly valuable, and they should be more neutral to our experiences, and not biased towards whoever's got the lowest latency connection because they happen to live in the right type of metropolitan area. Because some metropolitan areas are terrible. I get better internet connections from home than I do from work in London, because London has a problem. It has too many people trying to use its network, for example.
It's really quick, Anthony, before we move on. But how do you, as a researcher, able to continue sometimes with problems like whether it's an app store or a company with a headset not allowing people to sideload, like Quest, for example, or taking data? So as a researcher, I mean, we don't want to create an entire operating system, but are those big challenges that you find having those restrictions?
Yes, it's harder to talk to the general public. Yeah, there's no question about that. Delivering our experiences, our test experiences to people we would like to test them is harder. Yeah, there's it just requires more steps, more instructions, and we get a higher refusal rate. Partly because there's more steps, partly because some of those steps look like you're trying to break something. Because it is side loading, right? I mean, or it is download this zip file, and Norton antivirus goes mad because it's never seen it before. So yeah, there are those hurdles. yeah, some straightforward testing platforms would be good, but then obviously the only fallback then is reliable sandboxing, which I think is still an outstanding issue with apps on most platforms.
Thank you. Paul, you want to comment about this?
Yeah, the original question was engagement with community around kind of our take on things or what we're trying to do. And, obviously the upcoming headset with the bioanalytics, as we call them, or biometrics plus analytics is pretty interesting for us. We're already engaged with a lot of commercial partners around experiences such as the Pixel VR I mentioned, which was the OSHA safety training, but also with Thea Interactive and quite a few other companies. I think a total of 50 or 60 now, but love to be involved in the research with the research community as well, including, starting with you, Francisco, and we've already had side discussions about headsets, but glad to talk to anybody. We'll have a program once these start shipping in bulk, and love to start engaging with research folks. And a lot of it would be around either expressivity or cognitive load aspects, which we're kind of focusing on first. So you're muted, Francisco.
Yes, thank you. Thank you for that, Paul.
Yeah, sure.
The talking about interfaces, I have two screens, so the travel from my mouse from one display to the other, it takes a little bit to mute. I should use the shortcut, which I think is Control H or something.
Space bar, I think, or something. Yeah. So,
but and Greg, last but not least, I mean, I think that Cable Labs doing so much research. What do you think will continue enabling that research and your relationship, I guess, with researchers, but also industry, in terms of this particular problem, which is collaborative environments, ideal in 3D, but anything that you have will be quite useful to know.
Yeah, we focused quite a bit over the past few years on online gaming as being a set of applications that are pretty important for residential broadband users. And obviously there are a lot of commonalities between collaborative environments more generally and multiplayer online games. But I think we have had less interaction with researchers who are thinking maybe outside of the bubble of gaming. Thinking of some of the presentations that I saw today around training and other collaborative spaces, social interaction, that kind of thing, where there is more than just a player character, that first person shooter type of environment. And so I think there's certainly an opportunity for further interaction with those of us who are working on the network architectures that are intended to support these future collaboration environments, and those who are actually developing them. So I think it's been a good experience for me to be exposed a bit more to that than I had been in the past, and certainly would love to collaborate with some of the folks who have been involved.
Thank you. And actually, and if there's any question, we have a little bit of time left still. I'll start with what you said, Greg, and then we'll go in reverse order. Now, is you mentioned video game, or let's think about multiplayer game. I mean, the same thing that we see nowadays with so many of the games, and I believe Anthony mentioned the 2008 games. I remember even earlier with very bad experiences, the Dreamcast could connect via the modem. But did you see what are the differences, if there are any, in your opinion or your expertise, between a 3D video game that may be being used in a VR environment or non-VR with a VR application, which in many cases they have similarities. I mean, there are these 3D graphical scenarios. They may be used for training. They're game-like in some cases, not all of them. Um, what are the differences? I mean, can we just plug in whatever we do from multiplayer and use that, or is there things that are still outstanding? And I'll start. You can start. We'll move to Paul, and we end with Anthony. And thank you.
Okay. Yeah, I think the type of information exchange that goes across the network, and we've kind of come up with these two buckets, right? That I talked about of essentially sparse applications that are sending very low data rate and don't typically adapt to network environment, but it could be advantaged by having a low latency path, and high bandwidth capacity seeking applications that similarly want low latency but have the ability to adjust their sending rate on the fly. And it strikes me that some of these collaborative experiences might be falling in a kind of a middle ground, right? That it's not the cloud rendered video stream that you want to deliver at high data rate, and it's not the 100 kilobit per second, 200 kilobit per second, a state update packet, 60 packets per second, but it's a bit more than that, and so that kind of middle space where it seems like that there could be some discussion around ways to optimally use a network to enable low latency, keeping those applications in mind, right? That you've got maybe layers of information to exchange, some maybe more critical than others, and maybe less ability to react in the way that a video codec does, right? By adjusting its codec parameters. So that's for me, maybe perhaps an interesting problem that's unique to these collaborative environments that's different from traditional online games.
Okay, I'll take a crack as well. And wait for Anthony's excellent answer, but I'll give you mine first. It seems like a lot of the commercial use cases, pretty good breadth in what you're trying to do in a collaborative environment. And when you think about games, I have a stereotype for gaming, VR or otherwise, around first-person shooter-ish kinds of environments and so forth, which is incorrect, I'm sure. But there's a lot of variety in the commercial applications of collaborative immersive tech, including working around an object and examining an object. So if you remember the Virtualytics example I gave, people were pointing at things and sharing opinions. So a lot of visual, but mostly verbal communication around objects. And a lot of the product design architectural workflows would be similar, I think. It feels kind of fundamentally different than most of the games I would stereotype. In terms of you're not trying to hurt another person or get to the top of the mountain or whatever, but you're trying to have some insight around some aspect of something that's been created. So that to me feels like kind of the fundamental difference in terms of what that means in terms of the experience for the people. I think a lot of communication is nonverbal, obviously. Some people say, without quantifying or qualifying, greater than 80% is nonverbal. So I think having expressivity when people are engaging in that way is super important, and that may not be as true in many games. So that's a guess.
Yeah, I'd add two things. One is one of the things that VR tends to emphasize over games is the synchrony between video, audio, and action. My test case for that is somebody going, look at that, and where the synchronization needs to be within a few frames, 1 or 2 frames, and that's difficult at a networking layer at the moment. There are timing systems you can use, but it gets onerous quite quickly. The second thing is that games aren't simple. So I think the social VR system and the things like non-verbal, they're sort of relatively straightforward on the network terms. You're moving quite fast. The thing that games try to do is try to be fair for millions of users. So if you go and look at some of the code around games, you'll see there's so many edge cases. So I think, I've got a talk, it's quite long, but I post it in the chat, which is the debugging of Halo Reach networking, which is fascinating. Just go and listen to some game developer talking about exactly how they made it stable, because it doesn't need to just converge, it needs to do it observably fairly. And fairness in the game and turning it into the networking is a really fascinating problem, because the game has a very strong notion of equitable outcome, to do with latency and speed, and not prioritizing somebody over another one, which are all easy ways of fixing the problem, unless there's a time penalty, which you don't want. So they actually, I don't want to say that they've got an easy job. I would say that games is actually a really hard thing, and social VR systems haven't got to that stage yet, but we do have other problems that we have to deal with, like the synchronization between different media. But yeah, so I agree with everything else that was said. It's an interesting problem, and yeah, there are these competing requirements on the network, which you will come across when you go in this area.
Thank you so much. There's one last question. I'll ask this last question. Is from Christina. Before I ask the question, just to remind everybody, we're going to go into a break. I'll let you know how long the break is. Then we have our closing keynote, which is Mark Billenhurst. And then we'll be closing the conference. As I said, this workshop is, to talk about this and discuss research papers, but some of the organizers are involved on a planning grant that involves trying to find out what are the needs of the community, to see if National Science Foundation will want to give us money to build those tools or infrastructure. So we are going to have some working groups, and we do have some funds to pay people in the working group. So if you're interested, email me. I'll be reaching out to some people. We haven't started the working group. We plan to have one for AR/VR, one for networking, and one for machine learning / vision. The last question by Christina, if I pronounce your name correctly, please, I apologize, has Vasilevska asked, has anyone had experience with co-located users and robots? And I would expand this if one of you can answer, because we're getting close to the end. Distributed, we can also think about remote users and robots in terms of collaboration. So if anybody would like to answer this question, any comments? I think she's just looking for comments and experiences you may have had or know about. Anyone that
again, I can say something. So yes, it's a very, very hard problem, and teleoperation and robotics is a particular niche thing about which an enormous amount is known in terms of networking. It's a very specialized domain because there are some very, very valuable applications of it. Another thing to watch out for would be that one of the upcoming X prizes is about Avatar, is about connecting VR to robots, and I have a vested interest because I'm one of the judges. They suddenly realized it was VR to robots, and they'd hired a whole bunch of robotic judges, and nobody knew anything about VR. So I went in and was disruptive because I sort of introduced terms like co-presence and feeling as if you're in the robot and so on. So that's to watch out for, because there's going to be this summer. That competition's reaching its semi-final stage, and there are some really very impressive remote robot systems in that competition.
Thank you. Susmin, you have a comment or a question because you raised your hand?
Yeah, I had a quick question. Sorry. I know Francisco said this is the last question, but I was thinking if there is any role of caching or pre-computation in speeding up either the rendering or the interactions in AR VR.
If you consider the VR to be a sort of a streamed world, then yes, if that fits the web context, obviously game engines have to stream from disk or from somewhere. So they are for large worlds, they are predicting where you're going. And yes, that would work in a multi-user context as well, that you'd need to pre-cache, preload models. But I can only think of that, interpret that in a sort of relatively straightforward. The game engine needs to load assets from somewhere, and therefore they need to be available, because otherwise you stall. And obviously the one thing that VR definitely doesn't want is loading screens. So yeah.
So thank you. I'm gonna go ahead and share what's coming up and tell you about the break. Where's the PowerPoint here? I think it's this one. I want to thank the panel again. Thanks Anthony Steed, Paul Martin, Paul Martin and Greg White for a great panel, a great Q&A session. If you have more questions, ask them in Discord. I think Greg and Paul are not going to be in the conference, but I'll relay it to them. A reminder, I have sent the links for survey 1 and survey 2. These are for people that are in the workshop. Feel free to fill them. There's going to be some money prizes for it. And you don't have to complete them right now. You have time to complete them because I know all of you are extremely busy. We're going to go now into break until 19:15, so 7:50 GMT, which I believe is, at least my time will be 1:50 Mountain Time, and you can calculate your time zone. So we're going to have a break, and then we have the closing keynote, Mark Billenhurst, to talk about a great topic. So I'll just
Oops, got frozen, I think. Can't hear Francisco anymore. Is that me or is that Francisco? Or
it's not just you.
I can't hear him anyway, so yeah.
Okay, yeah, that's what I thought. I saw eyes moving around and so forth. So okay. Anyway, thank you all for coming. It was a great panel. Really nice meeting you, Anthony and Greg. So cool. We'll see you guys
Thanks. Yeah.
sometime in the future. Cheers.
Same. Thanks.
Thank you.
sorry, I pressed the wrong button. I would say one of our organizers does human robot interaction, and he's interested on the collaborative AR VR. His email's on the website, Daniel Safir from University of Colorado at Boulder. So feel free to reach out to him. I don't think he was able to make it today, but since you were interested on that topic, we'll go into a break, and thank you so much. to that time because some people may be coming to um, expecting the keynote to start 7:55. So again, thanks everybody for being here. People that may have already departure, thank you so much. Um, and the people that are here, I think we have a great keynote. You are reminder that we have two surveys that if you can fill in, it would be great. They have great prices. Um, eh, so survey one and survey two, and I'll be reminding people in Discord. If you're raised here in the conference, you can continue the conversation in Discord, and this will be the videos will be released by IEEE VR. That's my understanding, and right now they're also being streamed. So there's actually a lot of people watching. Well, I don't know if it's a lot, but between 10 to 50 people has been going up and down, or 10 to 40 in Twitch, and we also I think we're being streamed by YouTube. So I want to introduce Mark Billinghurst now. Mark, are you in? Yes.
Oh, yes, I'm here. Let me just turn my camera on, and now you can see me. There we go.
That's great. So Mark Billinghurst is the director of the Pathetic Computer Laboratory and professor of the University of South Australia in, I don't know how you pronounce this, Adelaide?
Adelaide, yeah,
Adelaide,
close.
Australia.
It's very close.
Also the University of Auckland in Auckland, New Zealand. Here his PhD in 2002 from the University of Washington and conducts research on how virtual real worlds can be merged, publishing over 550 papers in augmented reality, virtual reality, remote collaboration, and pathetic computing and related topics. In 2013, he was elected as a fellow of the Royal Social Society of New Zealand. In 2017, he was given the Ismar Career Impact Award in recognition for lifetime contribution in AR research and commercialization. And if you're in the field, then you probably know Mark Billinghurst. For me, it's really an honor to have him with us today. To me, he's one of the top 5 AR researchers that we have in the community, and I'm really looking forward to this talk. And the whole theme of this workshop is being how do we continue working and improving collaborative environment, and Mark has a lot to say about that. So without further ado, I'll welcome Mark to be the closing keynote speaker, and please write your questions in the chat on Discord. And thank you, Mark, for doing this, and take it away.
Great, thank you so much. I'm just going to try and share my slides, and hopefully it will go okay. Let me just see if I can do the screen share. And okay, can you see that okay?
Yes, yes.
Excellent, great, thank you so much. I've got quite a lot of material, but we'll see how it goes in terms of getting through it all. So what I'm going to talk about today is communication models for AR and VR remote collaboration. And so one of the themes of this whole workshop has been about communication. And of course, we know that communications are really important. John Pierce says that communications is not only the essence of being human, but a vital property of life. So of course, over thousands of years, people have developed different tools to help us communicate because of that, all the way from cave paintings thousands of years ago to mobile phones and the modern kind of multi-channel communication where you've got social media tools and everything else. But when we use technology in communication, sometimes it changes the impact compared to face-to-face communication. So for example, here's a typical face-to-face collaboration session. You can see some architects around the table, and they're sharing a number of audio cues, visual cues, and also interestingly, they're pointing to objects in the environment, models and pictures, things like this. So all of these communication cues play together. But you can see, in this case, the task space where they're focusing on is a subset of the communication space. They can see each other to some extent, at the same time as they're looking at the objects on the table and the pages. But when you introduce technology into the mix, sometimes that changes. So here's, some people sitting around a table looking at a screen. In this case, the task space on the screen is separate from the communication space. It's quite hard to see each other's communication cues while you're looking at the screen. So of course today there are many different teleconferencing technologies available, and with the COVID situation the last year and a half or so, people have experienced many of those things, and you have that same separation happening as well. So here's a typical teleconferencing setup where you've got some chemists sitting around talking about a chemical molecule with their collaborators, and you can see again you've got this communication seam between this task space and the communication space. So you can see that with current technology, there's some limitations. We have a lack of spatial cues. When you're looking at somebody on the phone like this, the person's face kind of blends into the background video. You have the poor transmission of communication cues, limited gaze and gesture, nonverbal communication. And as I just talked about, this introduction of artificial seams between the physical and digital world. But with AR and VR, we can overcome some of those limitations. So, of course, we've all seen a variety of online social VR experiences like Outspace VR or Facebook Spaces. And then there's also a variety of collaborative experiences in AR where you can bring virtual people into the real world to share the same real space as you. A good example of that is the software from Spatial, Spatial.io. And the Spatial platform allows you to have a collaboration in either AR or VR or across desktop or mobile platforms. So I'm going to show you a little video of this working now.
What if there was a better way to collaborate? A better way to build and work together? A way that brought us closer, as if we were sitting next to each other, face to face. What if our creativity could burst to life in the space around us? As a collective computing environment that lets teams visualize their thoughts in the room around them.
Hi, Mike. Hey, Jeff. How's it going?
So whether you're on a desktop computer or scribbling notes on your phone, all your digital devices are seamlessly tied together into an infinite workspace. You can manifest your ideas before your eyes by just saying them, and in a click, expand them with the power of all the world's information. Using augmented reality's infinite canvas, pixels become tactile, letting you manipulate them like clay.
Hey, buddy.
We believe digital and physical worlds should live in harmony together. You can sketch ideas out on paper, or have them exist digitally. Spatial brings people and ideas together into a single shared environment.
Okay, I'll stop the video there, but you get the idea. So you can see in this case with Spatial, you've got a virtual person coming into the remote, into the meeting remotely, and they feel like they're in the same real space, and they can do things like load up 3D models or show content. So augmented reality allows us to break that communication seam. So there's a task space, and now we can see each other at the same time as we can see that 3D model. Most recently, last week, some of you may, or 2 weeks ago, I guess it was, some of you may have seen that Microsoft released the Microsoft Mesh platform. And so this is going to be a platform that should enable us to build a wide variety of AR and VR collaboration experiences. So this is very, very important, but it turns out that there's been relatively few people in the academic community that have been studying this. There's been in terms of AR, there was a publication that I wrote a couple of years ago that summarized the last 10 years of the ISMA papers, publications, and we found that out of all the 520 or so papers that were published at ISMA, full papers, only 9 of them were talking about collaboration. So it's less than 2% of all the papers at the leading AR conference. And then similarly, not only there are a few papers being published in collaborative AR, and but also there's few user studies being done in this space as well. So a couple of years ago, I also co-authored a paper reviewing the last 10 years of augmented reality user studies, and we found that fewer than 10% of AR papers had a user study, and then only 12 out of the almost 300 user studies were user studies around collaboration. and only a very few of them use head-mounted displays, so providing kind of full AR experience. So this slide shows that picture there. You can see the graph on the left shows the number of AR papers that we were able to find over the previous 10 years. These were papers that had significant impact, so they had an impact score of, or average impact of 2 or more. And then so the blue is total number of papers, and the green is number of papers with user studies, so very small. And then the right-hand side picture, a bit more complicated, but the second gray bar from the bottom, this is the number of AR papers with user studies in them compared to all user studies, so it's at less than 5%. So that shows us that even though collaboration is a really important, increasingly important topic in terms of usage, there's relatively few papers that have been published in that space, especially in the AR space. I don't have the same figures for VR, but I suspect they're similar, and also relatively few studies that have been done. So what I want to talk about today is a little bit about communication models, and then talk about how we can use those communication models to guide the user studies that we might perform, and hopefully by doing that produce good outputs that will increase the usability of collaborative experiences. So first of all, talking about communication models. So some people think that when people communicate, it's kind of like this, that the person has an idea in their mind and talks about it, and the other person understands what they're saying, and they both share the same idea. But actually, communication is a lot more complicated than you think. So there's a lot of factors that come into that. You know, somebody has a thought and starts communicating. There's some external influences that may make it more difficult to understand what the person's saying, and then you have to reflect back to what you said to the original person. So communication has been studied for a long time, and probably one of the most famous communication models is the model Claude Shannon developed in 1949. This is the Shannon-Weaver model of communication. And in this case, you have an information source, and then that information source encodes information to a message. The message that then gets sent through a communication channel that's received by some technology that decodes the information, and then you have a destination for that message. So you can see from here, and in addition to this kind of linear communication pattern, then you have external noise that may have some influence as well. So Claude Shannon developed this while he was at Bell Labs, and of course they were very focused on telephone communication at the time, and so this is very much almost like a string telephone model, where it's pretty much one-way communication, and the signal depends on the channel, so what technology you're using to send the signal, and what noise there might be in that channel. But it's a fairly limited communication model. It's very linear one way, but it has some key components in terms of the channel capacity. So different technologies may be able to communicate high bandwidth. It also includes the concept of noise, and how that different technologies may introduce noise that may corrupt the signal. So that was 1949. In 1960, Berlo developed the SMCR model, and this stands for the source, message, channel, and receiver model. And in this model, it included more contextual cues. So for example, the source most likely would be a person who's communicating, and the person will have some knowledge, also have some cultural biases, they'll be part of some social system, and have some level of communication skills. And all of those things together impacts how they might encode the message. And then the message is encoded in terms of content and number of elements, and that includes how you propose to communicate the message, like verbal and non-verbal behaviors. That's communicated through a channel which maps to the senses that people have, and then somebody receives that message and they decode it. And again, when they receive that message, they understand the context of that message or they understand the message in the context of their culture and communication skills and knowledge. So the innovation he brought in was to think more about communication in terms of context, and how messages could be communicated using multiple channels and multiple components. But his model is also limited because there's no feedback in this model. Communication, again, is still a one-way linear communication model. He also didn't include any noise anymore. So a simple example of the SMCR model, this is from a paper that Susan Fussell wrote last year, and she talks about in this paper what happens when the channel corrupts the message somehow. So in the top line, you can see a message a communicator wants to send a message about happiness, so they're feeling happy, they send a happy emoticon, but somehow on their mobile phone, the emoticon gets corrupted and the face that's actually sent is an angry face. And so on the receiver side, you know, they receive a message of anger, not happiness. Compared to the second channel, in the second example, the person sends a message of happiness, and you know a happy emoticon is received, and the receiver understands the person's feeling happy to some extent. So around the same time, Shram and Osgood developed a circular communication model, and the key features of this is that the encoder and decoder were the same person. So, and it introduced the ideas that people were, so the sender and receiver is the same, and communication is also circular, and feedback's a really important feature. So I send a message, and then when you interpret the message, it gets sent back to me, and I interpret your response and so forth. But one of the problems with his model is that there's no noise in the model, and also he viewed messaging as very much a sequential process. So, you know, I would send a message, and then I would wait, and you'd send a response, and we'll go back and forth like that. But the key feature, one of the key features I said was it's a very dynamic model, so we can have this continual circular transmission of messages. And then in 1970, Barnlund developed this transactional model. And this is a very complicated model, so the picture there looks very confusing. But the main features of it is that he imagined communication as a multi-layered process and with multi-layered feedback, and also a continuous process. So people will be sending and receiving it at the same time. So as I'm talking to you, you might be giving me communication messages at the same time. You know, if I'm saying something and your face expression starts changing while I'm speaking, then you're communicating at the same time as I'm communicating, communicating response. He also talked about how there's multiple types of communication cues. So there's public cues, which are things in the environment. So previously I showed you the example of the architects collaborating around the table, and you can see objects on the table and pictures. So that's an example of public cues. There's also private cues, which is basically the sensory feedback you're getting. And there are behavioral cues, which is the user's actions, both non-verbal and verbal actions. His model also included noise and filters, and then also included a number of contextual cues, similarly to what we'd saw in the SMCR model with social, cultural, and relational cues. So a lot of the communication models developed since then have all been based on Barnlund's model. But I see this picture is kind of complicated, so a simpler version of the picture might be like this. So you've got two people that are trying to communicate, and one of the key elements of his model is that people co-create meaning in communication. So as they start talking to each other, you have communication cues being shared, you have cultural cues being shared, and contextual cues being shared. You've got noise coming into the mix, and together, by using multiple communication channels, you can co-create the meaning. And then another innovation that was introduced in 1991 by Herb Clark and Susan Brennan was the idea of grounding. And their idea extends a little bit what Barnlund had said. They viewed communications as a collaborative action. So people work together to try and achieve common understanding or common ground. So you can see on the right-hand side some examples of some short communication clips. So the second one, for example, the person says, "How would you describe the color of this flower?" And the person they're talking to says, "You mean this one?" and points. And the other person says, "Yes," and they say, "It's off yellow." So you can see in that case, the person who was listening wasn't quite sure which flower they're referring to, and used a pointing gesture to clarify. And then they got the yes, which is an example of a back channel, and then they were able to get to some common understanding. And then the quote below is a little bit funny. It's from Groucho Marx and the Marx Brothers. And Mrs. Dimple says, "Where can I get hold of you?" And Chico says, "I don't know, lady. You see, I'm very ticklish." So you can see it's kind of funny because he totally misinterprets what she's trying to say. And then Mrs. Dimple says, "Well, I mean, where do you live?" And then Chico says, "Oh, well, I live with my brother." So in this in this model, conversations are collaborative action. People try and work to achieve common ground, and there's a few key steps. People in the conversation make a new contribution, then there's some acceptance or back channel showing whether or not the person has accepted, understood that information, and if not, there's a clarification step. So you can see in the second example I read about the flower, the person said something about a flower. The person they're talking to wasn't quite sure, so they gave a back channel and they asked for clarification, and then B gave another back channel, which is yes, and then they were able to receive some agreement. The other important aspect of their model is that they basically felt that people were lazy when it comes to communication, and so there's theory of least collaborative effort. So people try and minimize their total effort on collaboration and contribution. And so they try and say as little as possible to achieve a common ground. And then the final point is that technology can present barriers to this grounding. So, for example, if you're having a phone call, obviously on the phone, you can only hear the person, you don't have any visual cues. So as I'm speaking to you and if you're feeling confused, you know, your face might be showing confusion, but I can't see that because I'm speaking to you. So sometime in the conversation, you have to say something to show me that you're confused. Compare that to audio or video conferencing. On video conferencing, of course, you can see the person's face, and so there's less barriers to grounding. So he said that there were several constraints for this grounding behavior. You know, in face-to-face setting, we have co-presence, we can see each other. There's visibility, we can hear each other, things are happening at the same time, and there's simultaneous actions. So there's very few constraints or barriers to grounding. But then using a telephone call, you can't see the person, you have very low sense of co-presence. And then you've got things all the way down to like email or letter writing where you don't have simultaneous feedback, and so it becomes very difficult to perform grounding because you've got to wait for responses. The final thing I want to mention while this is being developed is that in the media space, Daft and Lingle developed this idea of media richness theory. And the idea is that we have communication channels that we can use, but some communication channels vary in their ability to convey communication cues. So for example, face-to-face communication is very, very rich, but when you write a letter, the amount of communication, in terms of the communication cues it can convey, it's very low. And so their theory is that richer, more personal communication media is more effective for communicating. So you can see the little chart there shows a number of different types of communication mediums, from, you know, posters, which are very impersonal, to letters, all the way up to video conferencing face-to-face. And on the left-hand side, it becomes increasingly more effective. The other interesting aspect of their theory is that sometimes you have to fit the communication medium to the task. So, for example, do we need to have a face-to-face meeting to find out what the weather is? You know, I can just look on my phone and find the weather. I don't need to have a face-to-face meeting with the weatherman to find out my weather. Or if you're about to propose to your partner, you know, would you propose to your partner over text, or would you propose face-to-face? And most people would say, you know, they'll propose face-to-face because it's an important decision and they want to make sure they've got really clear communication cues. So they produce this chart here, and on the chart you can see on the bottom side the task complexity from low to medium to high, and on the left-hand side the richness of the communication medium from low to medium to high. And so what they're saying is that there might be some times where you've got a very low complexity task, like finding out the weather or completing a mathematics problem, and you don't necessarily have to have a face-to-face meeting for that, and it becomes an overcomplication. It's too much information is conveyed. Conversely, you might have a very highly complex task, like negotiating a business deal, and if you're trying to use letters for that, then that might become an oversimplification, and you may not be able to complete the task very well. So you have this band of effective media use, and that's really important when you start thinking about how you can apply communication models to AR and VR studies, because sometimes with AR and VR you have too much communication cues and you may be overcomplicating the task. So I've just talked a bit about theory, so just to sum up, you know, there's been an evolution in communication models, and communication by and large is very complex, continuous and dynamic. There are multiple types of communication cues that can be shared, from the surrounding environment to your body sensors to your behaviors. And the participants try to co-create meaning using grounding and using least effort. And then when you start using technology for communication, the communication channels can affect that grounding. You know, you may not be able to communicate as effectively. Different communication channels have different richness of cues, and you also need to fit the channels to the task. So let's talk a little bit now about how you can apply these communication models to AR and VR and to collaboration. So here's a very simple communication model. We just got two people that are talking to each other, and you know, there's a message that they're transferring. There's some noise in the message. There's some feedback happening. But you could imagine that, and you can imagine this might be a phone call, for example. So it's just on the phone. But you could imagine if we could add more technology, we might be able to change the nature of the communication. So, for example, you might be able to share a video, and so then you can see the person's body position, and you could have things like mimicry that shows that it creates some sort of empathy, or you might have some technology that allows you to remotely share gaze, and you know that might have some impact on the collaboration as well. So if we look at AR and VR, this is a very common setup. This is in our lab. This is a system for remote collaborations. So the person can wear a pair of smart glasses, a AR display with a depth sensing camera on their head, and they can do some tracking. And so here you have a picture on the left-hand side of a person in the AR display. The right-hand side is the remote user. The remote user is using a mouse to draw on the video coming from the person. And on the left-hand side, the AR person can see that annotation appearing in the real world. So that's pretty common. There's many commercial products now that have this kind of remote expert, but there are some questions you might have about that. So for example, you know, do we really need to share video of the remote user's space? How does this remote collaboration compare to face-to-face collaboration? What's the effect of having that pointing cue, and what other communication cues could be added to, and how might that affect the collaboration? And so there's some predictions you could make when you look at this type of setting. You know, one would be that remote collaboration may take more time because you don't have the same richness of communication cues as face-to-face. If you've only got an audio condition, if you don't have any visual cues, then people might speak longer because they have to describe everything using words. And if you can see a person's workspace and have good spatial awareness, then that may reduce the communication needed. And so that might also change the communication process. So these are the type of predictions you can make when you consider the communication cues, the models we've been talking about before. So a good example of this, of how it might be applied, is a paper that Susan Fussell wrote in 2000. And in this case, she had a person that was repairing a bicycle, and the person, you can see on the left-hand side there, they have a camera on their head and a small head-mounted display. And the camera view was shared to a remote user, and the remote user could then, in the head-mount display, they could see some steps for the bicycle repair, but the remote user could see the camera view and could talk to them while they're repairing the camera. So they really want to look at this sharing this video feed, how that impacted communication. And so they had three conditions. They had a face-to-face condition, an audio-only condition, and then a condition that had audio plus video. And most importantly, they performed a communication analysis on the communication behavior. So they recorded all the communication that took place, and then they did some analysis of the words that were spoken. So they did a number of survey to ask people's user preference. They measured the task performance. And as I said, they did conversation coding and measured communication quality. And on the right-hand side, you can see some of the results. So what they found was that the task communication, the task was much, much faster when people were side by side, face-to-face, which is not that surprising. But they also found that sharing the visual cues remotely significantly improved that communication grounding, because now people could see each other and they had a common frame of reference. And they did find it, as we talked about before, that when people were just speaking, without the visual cues, in the audio only case, they would have much longer sentences and to describe what was happening. sharing the video create this shared sense of workspace. So on the top graph there, you can see the performance time. You can see the audio only condition. It took much longer to perform the task than the face-to-face side-by-side condition, but the video condition still was slow. And then the bottom one is the percentage of deictic references made in that conversation. Deictic references are where somebody points at something and says, "What is that?" And you can see for the worker who's in the black, there was very little numbers of deictic and percentage difference in deictic references between the side-by-side and video case, but in the audio case it was much lower. So what that means is when they couldn't see, well, when the remote helper wasn't receiving any visual feedback, then the worker stopped using deictic references because he realized the remote person couldn't see their hand. So we say, "What is that?" and they're pointing with their hand. If the remote person can't see your hand, then you would have to change your language. So this is typical of a study you can do when you take a communication model and apply it to an AR/VR situation. Let me talk about another study which I did myself, which is a bit more VR related. And in this study, we wanted to look at what is the impact of task space separation. So I showed you that picture before of where you have the worker's task space, in this case doing a task on a table, as a subset of the communication space. And that compares to when you're looking at a monitor or projection on a wall where the task space might be separate. So of course, one of the main differences is that when you're looking away from each other, like at the wall or something, then you aren't aware of each other's communication cues as much anymore. So when you think back at the communication models we've been talking about, if I can't see clearly your face expression or your hands, then I don't get those communication channels coming through. And what that will could cause is that my communication behavior changes. I might use more speech in a different way, or it might take me longer to perform a task, or I might need more clarification about what you're talking about. So we wanted to do a task to explore that using augmented reality. And so this is the setup we had. So in this case, we had people performing a task that involved arranging building to solve a small puzzle. So they had 9 buildings in a 3x3 grid, and each building was different type. There was a church and a pub and a school, and there were certain sets of rules. So for example, the pub couldn't go next to the school. And so each of the participants in the experiment had their own set of rules, and they had to talk to each other to try and figure out if they could lay the buildings out correctly and solve these rules. So as I said, in the face-to-face case, you had model buildings. In the augmented reality case, you had cards. When we looked at the cards through a video see-through display, you saw AR models of the same buildings appearing. So you can see the augmented reality case and the face-to-face case are very similar in that the task space is a subset of the communication space, and the physical manipulation was the same, and that you had to pick up cards basically. But the third condition was a projected interface. So you can see on the far right, the 2 people are sitting side by side, and they're looking at the wall, and projected on the wall is a graphic image of the same buildings, and then we had a tangible interface. They could move around a tracking device to pick up and move buildings and place them on the thing there. But the main difference, of course, with the projected interface compared to the other 2 is now that you've got that separation between the task space and the communication space, because it's separated from you on the wall. So from our communication model, we should be able to predict that face-to-face should perform much better than AR and projected, because of course you have rich communication cues. But in the interface I showed you, you can see that the task space in the AR case is a subset of the communication space, just like in the face-to-face case. So you would feel that the communication patterns in AR should be more similar to face-to-face than the projected. And so what we found was that indeed performing face-to-face took a lot less time than in the AR or projected condition. But when we looked at communication behavior, we saw people use more similar behaviors. So in particular, we looked at the percentage of deictic phrases. So when a person pointed at a building and said, "What is that?" or "Can you move that building over there?" And we found, you can see it in the bottom right-hand graph, that there was a significant difference in percentages compared to between the face-to-face and AR in the projection case. So in the projection case, about 15% of the language was didactic language, whereas in the AR and face-to-face case, it was about 20 to 22%. And so there was, and there was no difference between the AR and the face-to-face percentage use of didactic. So the language patterns were the same. We also looked at the gesture patterns, and we found that they use the same gesture patterns in AR and face-to-face, and people felt using that tangible interface was very easy to use. So in this experiment, we showed that we could look at the predictions from the communication models, and we showed that the communication behavior aligned with those models. One of the things we learned though is that which we should have realized in hindsight, but there are significant perceptual issues with AR. If you're wearing a headset display with a narrow field of view, then you can't see your surroundings the same as if you're in face-to-face. And so one of our subjects said that collaborating in AR was like working solo together. The head mount we had a 40-degree field of view. And so when you're sitting across the table or standing across the table from your collaborator, occasionally you'd see the person come into view or the hands come into view, but you didn't have that same peripheral awareness you'd have in a face-to-face collaboration, which may have been why the performance was affected. So that was really interesting learning, is that collaboration is really a perceptual task as well. And if you reduce the communication channels and reduce the perception, that's going to have an impact as well. So going forward a few more years now, I want to talk about another experiment we did called the empathy glasses. And with the empathy glasses, we want to focus more on implicit communication cues. So with implicit communication cues, these are communication cues that we share in face-to-face, like eye gaze or face expression. And normally in video conferencing or even in VR, where you've got an avatar without much expression, you lose a lot of these cues. So we combined together 3 technologies to try and enable us to share that. We combined an eye tracker with an AR head-mounted display and some photo sensors called effective wear frames that could measure your face expression on glasses. So already I showed you previously a typical remote collaboration system where somebody wears a camera on their head and live streams a remote person. In that setting, because you can't see the person's face, you can't perceive their eye gaze. But with this setup, we wanted to be able to let the remote person know exactly where the local worker was looking. So we had this set up here. You can see all this gear on their head. In addition, the person wore a heart rate sensor, so we knew what their heart rate was. And then on the right-hand side, I'm not quite sure if you can see my mouse, but you can see the green dot there. The green dot is the remote pointer from the remote expert. And so, if I'm doing a task and the remote person says, well, can you move this object like this? Then they move the green dot around. But more importantly is the red dot, which is above that, just right there. And the red dot here is the eye gaze of the person doing the task. And so what this means is that if I'm the expert and saying, oh, move this block over here, I can tell whether they're paying attention to me or not because their eye gaze looks to the block. And so this changes the nature of communication from being explicit, where I say something and then wait for you to respond, to implicit. And going back to our communication models, this means that now we can have parallel communication happening, and it's much more synchronous rather than me having to issue a command and wait for your response. So let me show you the video of this. What you see here on the right-hand side is a person doing a block building task where they have to arrange a picture out of blocks on the left hand, and then there's the expert helping him. And so you can see now the expert is going to start moving the mouse around and telling him to move a block over here, and then he can see the eye gaze is following that, so they're paying attention. You'll also notice the heart rate, and then when they complete the task, their face expression will change because they start smiling, and the system picks up the smile. So there's technology to do.
Mark?
Yes.
Quick question, sorry to interrupt. Does the expert has a real-time layout of the pieces, or how is that happening?
Well, in this case, we didn't tell the expert how to lay the pieces out. We just told them that we gave them an object to build, and they had to then decide together how to build the object. So in this case, for example, he's building a boat. So he said, okay, now work together to build a boat. and then the expert would tell them, okay, let's put these blocks together. So there wasn't a picture to do that. But we've done other experiments where there is those. So I'll talk about that in this.
No, I understand, but the pieces, are you tracking the pieces and
No,
render on the computer?
no, there's no pieces tracking. These are just real objects. There's no pieces, and
Okay.
the expert's just seeing a live video feed.
Right.
So
Okay.
the only enhancements are the red and green dot you see.
I see.
So
Thank
that's
you.
the AR pieces. So that was a setup, and we did a user study, or we did a pilot study with this one, but we did a full study with another system. And in the full study, we had people assembling Lego blocks, and really wanted to look at what was the impact of gaze and pointer on remote collaboration. And so we had 3 or 4 conditions. One condition where you had no communication cues going back, apart from talking to each other and seeing the video. A second condition where the remote person could point. A third condition where the local person who's doing the work would send back gaze cues. And a fourth condition when the gaze and pointing was combined together. And what we expect, again, from our communication models is that when you've got pointing, that provides one communication channel, and gaze provides another communication channel. And of course, gaze is an implicit channel because people gaze unconsciously, whereas pointing is an explicit channel because you have to make a decision to point. So you'd expect as you provide more communication channels, then that your performance improve on the task. And that's what we, in fact, found. So you can see here, the graph on the top right is the performance time, and when we combine together the gaze coming from one side and the pointing from the other side, we've got a 22% faster performance time. Also, there was fewer spoken phrases, so we the bottom right graph shows the number of spoken phrases to achieve the task, and you can see when you're sharing the pointer and the gaze, then the pointer and the eye tracking, then the number of spoken phrases has gone down from 35 phrases to complete the task down to about 20 phrases. And people also subjectively felt more connected, and they felt they understood the partner more. They had a sense of co-presence, and almost 80% of people ranked the condition using the gaze and pointing together as their favorite condition. So they felt it improved quality of communication a lot. So another example of how you can share communication cues is between an AR and VR situation. So I just showed you between AR and, well, smart glasses and desktop, but using AR and VR, you can share a lot of communication cues sometimes you don't see in the real world. So we did a study to explore that, and particularly want to look at how we could share 4 communication cues: gaze, hand gesture, head pose, or where the person's looking, and also the body position. And we want to have a person collaborating between an AR and a VR situation. So you had a person in the real world who had to perform a task. Then we made a copy of that real world, a scanned copy, and we had a person in VR on the exact same copy helping them perform that task. So in the AR case, when I put my glasses on, I would see a virtual person standing beside me, and they would help me perform the task. A little bit similar to the video I showed you from the spatial.io. And so there's a collaboration between the AR and VR user. So in this case, we had, on the AR side, people use the HoloLens. On the VR side, they actually survive. We used the Leap Motion to capture hand gestures. So the communication cues we had, you'd see an avatar head, you'd see these hand gestures, and then we had 4 different ways of representing gaze cues. So the number B there shows just the heads together. Number C shows a view frustum coming from your head. So in the real world, you can only see where somebody's looking when you look at their face. But in this case, because we have a view frustum, I can look away from somebody, and if I can see the view frustum, I still know where they're looking. And then condition D is a head gaze line. So where we looked at the head tracking and we drew a line where they're looking at. And then finally, we included eye tracking, and we had an eye tracking line as well. And so we use it just on room scale tracking, and the task was for people to find objects together. And so in the AR case, you would see a bunch of virtual blocks, and the virtual blocks would have numbers on them. The VR case, you'd see a bunch of virtual blocks, but they had letters on them, and you had to find the blocks that would correspond to each other. So maybe you have to find the block A2, and the person in the AR case, we have to find the block with number 2, and the person in AR case would have to find which of the blocks with number 2 had A on it. So I'll show you a video of this working. So here's what you see. So in the AR case, you see this virtual head looking at you. You can see the pink view frustum lines, and there's the head pointing line as well. So so when I look away from the person, because when they have the view frustum visible, I can still see where they're looking. So that's a very important communication cue. And that's a communication cue you don't get in the real world, actually, normally. So you can get better in the real world. So you can see here is looking at these different blocks. As I said, in the AR case, you can see numbers. In the VR case, you can see letters. And then you have to try and pick up the blocks together and then put them in a certain place in the position. So in this little clip here will show I guess it's the end of it. So but going back to our communication models, we should think that using eye gaze or head pointing should enable you to work better than having no communication cues, because that allows you to see where the person's looking. And also, if you have eye and head pointing cues, like the gaze lines, that may reduce the need for pointing, because I don't need to point with my hands anymore, because you can see exactly what I'm looking at with the eye gaze pointer. And so what we found, first of all, is there was no difference in task completion time. And that's not surprising. With these collaboration tasks, one thing that you often learn is that people adapt their communication behavior to still perform the task with the same level of speed, but they communicate in very different ways. We measured how often people were looking at the same object, and we found that by providing those gaze cues, either the head pointing or the eye gaze, people would look more often at the same object, that's what the chart at the top is showing, top right. We found that people felt that using the eye gaze made it or head gaze pointing, I should say, made it much easier to complete the task than using just the baseline condition with no cues. And also the pointing gestures were reduced as we predicted. So you can see on the bottom there, the blue bars is the number of pointing gestures, and you can see in the baseline is an average of 3 pointing gestures per trial, but in the head gaze pointing condition, it's down to below 1. One of the interesting things we did find, though, is that there was no difference between having head pointing, head gaze pointing, and eye gaze pointing. And I think this gets back to what I talked about before with the media riches theory, in that eye gaze pointing lets you provide very fine-grained idea of where the person's looking. But for this task, you didn't need that. You just need to know within their field of view where they're looking. So head gaze pointing was sufficient. So again, this is a good example of how the communication models predictions match up to what we're finding in the behavior. And then the last thing I want to give you an example of is, actually second to last, sorry, there's one more after this, is what you can do, what happens when you can't see the person you're collaborating with. And we did an experiment to see what happens when we separate out the communication cues from the person. So of course, when you've got, in this case, on the left-hand side here, you can see 2 people in VR collaborating together. And, because I can see a life-size avatar, I can see gaze and gesture communication. But on the right-hand side, when the lady turns her back, she can no longer see me pointing because I'm behind her. And so, so we thought out, is there a way that we can still show those same pointing cues without her seeing my virtual avatar? And so I came up with this idea of this mini-me. And the idea of the mini-me is that you've got a life-size avatar, but when you turn your head away from the life-size avatar, a little miniature avatar will appear and will point at the same location in the real world that you're pointing at as a life-size avatar. And so it uses some of the same communication cues that you'd have from a life-size avatar in terms of gaze and gesture, but it's always visible. So you can always see those communication cues even when you can't see the person. So this is important because this solves some of the problems with, especially with AR communication. If you've got a HoloLens, for example, with a small field of view, it's very difficult to keep the virtual agent in view at the same time as the person. So let me show a little video of this working. So you can see here with a limited field of view HoloLens, you can't see the agent at the same time. Here's the agent there. And if I turn away to look what they're pointing at, I can't see them anymore. So the idea of the mini-me is that when you turn away, this little miniature guy appears and keeps on pointing in that same direction. And so you can see that person pointing on the box. So here's the example of the box. When the person's behind you, a little miniature person appears in front of them and is pointing at that box in the real world, showing the same communication cues as the large life-size avatar. And so we did a study of that, and what we found, we looked at two different types of tasks, and what we found is that using that mini-me produced a 20% performance improvement, and that's because you had those communication cues always visible, which again gets back to the communication model where you don't have those cues anymore. It also produced a higher sense of social presence because you could see that person all the time, and users preferred to use it. Most people felt the task was easy to complete, and in one experiment, 60% preferred it, another one, 75% people preferred it. So the last example I want to talk about is one we've just recently finished, looking at using spatial audio and visual communication cues. So if you're looking at large-scale collaboration, so for example, you've got a remote person trying to communicate with somebody over a large office scale, can you use spatial audio and visual cues to help convey some communication channel information? So our experimental environment was, this is a floor plan of our office, and you can see for most of the office, we had somebody walking around with an AI headset, and the task was to find objects in the office space. And then in one of the office rooms, we had a person standing in VR, and in the VR space, in the VR room, they had a copy of this large office space, a scanned copy again, and so they could move through that in VR, and their goal was to guide the person to the target objects. You can see the little red squares there. These are Lego blocks that are placed around, and so the goal was to try and find small Lego blocks placed around in the object in the space. So you had a remote person in VR trying to guide somebody in AR who was using the Magic Leap display, and that to try and find their small Lego blocks. And so you had a local remote person, and they did that by using their handheld controller, so they could point with the controller, and then the AR person would see that pointing. But also there was spatial audio beacons coming from the object. So when you had the AR head display on, you'd hear the spatial audio from the object, and you also shared back the video from the AR worker back to the remote person, so they could see their video, and they could also see where they were in the model. So let me show you a video of this working.
Mixed reality remote collaboration systems have evolved over years, but most research has been focused on visual cues. We introduce a system that shares both visual and spatial auditory cues. We conducted a user study to evaluate the system and found that spatial auditory and visual cues help in efficiently completing collaborative search tasks. Here are a few examples.
Hey, so this object is here.
Okay. I feel like I'm getting closer to the object. Is it this one?
Yes.
Okay.
So I'll stop the video there, but what you saw is them using spatial audio, and you can see on the right-hand side was the VR view with a live video insert. The left-hand side was the AR view, and actually in the VR view, you also saw a red ball appearing, which was the head of the AR person. So we performed 2 user studies in that case. One study was focusing only on audio cues, looking at how spatial audio could help us, and whether the spatial audio beacon was more useful than just the spatialized voice or not. The second study focused on adding visual cues, the view frustum of the remote person, and also hand gestures. So here's one of the visual cues, the hand gesture, and there's the view frustum appearing as well. And so what we found was we took some measures in terms of task completion time and some subjective measures of social presence, and we also analyzed the communication. And we found that using the spatial audio cues, so having the person speak to you, significantly improve this sense of spatial presence versus non-spatial audio. Most participants preferred having the spatial audio beacon, and the spatial audio beacons also produce significant differences in the back channel utterances. You can see it on the chart here on the left. The second column is the percentage of back channel feedback that's been given, and you can see 3 and 4, which is the gray and brown. These are the two conditions that use spatial beacons, so the audio coming from the location of the Lego blocks. And you can see, in this case, they're significantly lower than the amount of back channels given in the non-spatial beacon condition. And that basically is because the local worker, for example, was more easily able to locate the target, and so didn't need to give back channels to confirm and perform that grounding that we talked about before. And the second study was looking at adding that virtual view frustrum and hand gesture cues, and what we found that adding both of those performs significantly faster. The top chart here shows the performance time. This H4 is where you've got a virtual head of the remote helper and a virtual hand, and this is significantly lower than H1, which is where you don't have anything, just the audio by itself. And then also increased social presence. And when we did the, but there was no difference in the communication pattern. And I think that's because there was very little difference in terms of communication cues people used. So just to wrap up, I've given you lots of examples now of how you can apply communication models into user studies. And as I said before, there's been actually very little user studies done in the AR, VR space that use communication models. So hopefully this gives you some idea of how you can do that. There's a lot of technology trends happening though that are really, really interesting. So of course, many of you know about these towards high resolution displays, towards being able to capture space in real time, natural gesture interaction, eye tracking, and emotion sensing. We've already had Paul from HP talk about the HP OmniSet and how this hardware will allow you to connect your eye gaze with pupillometry and heart rate tracking, so you can provide a rich, capture a rich set of physiological cues from the user, cues that you wouldn't normally have in face-to-face communication. And then you've got technology like the Lucid Link, which has EEG sensors in the faceplate of the VR device. So now you can measure brain activity. And so what this means is that you can actually capture cues that you wouldn't normally have in face-to-face communication. And this could enhance communication even further beyond what you might have in face-to-face. So as an example of that, we've started a new project on brain synchronization. So it turns out there's a really interesting phenomenon happening when you have people perform the same task in the real world. So here's two people sitting opposite each other, and they're pointing at each other with their fingers. And as one person starts moving their finger around, the second person starts following the finger. And when people do this kind of finger tracking task, what sometimes happens is that the electrical activity from the brains becomes synchronized, the phase of the electrical activity. And when that happens, people report they feel very much in sync with each other. They feel like they're communicating very clearly, and they feel like the other person can understand what's happening. So here's an example of what that looks like. This is the black dots here are the EEG electrodes from each of those people's heads. This is before they start doing that task. And so they track their fingers around, and then they stop moving their fingers. And while their fingers are stopped, you measure the brain activity again, and sometimes you see something like this happening. And so these arcs you see here show the electrodes which are in phase sync with each other. And so even though the people aren't moving their hands anymore, because they've done this task that gets them in synchrony with each other, their brain activity starts becoming synchronized. So we saw that, and we decided we want to reproduce that in VR. So here's two people doing that task in VR. This is a paper we just published a month or so ago. And so you can, of course, because they're in VR, they don't have to look at each other anymore. So this is what it looks like in VR. You can see an avatar. You can move your hand, and you try and move your hand in collaboration with the avatar and keep pointing at the same as the other person's avatar. But because you're in VR, you can do things you can't do in the real world. And in particular, you can put yourself inside the other person's body. And so here's an example of what that would look like. So now both people in the same body, and again, you're trying to track the other person's hands. You look down and you see two pairs of hands coming out of your body, and you have to move together. And what we found is that, well, before you start doing the training, this is the electrodes, and the lines between them show the electrodes which are in sync with each other. But there's a relatively low level of connections. This is mostly just due to randomness. But once they've completed the task, we see these thick red bands now, and this shows that there are 4 or 6 electrodes that are connected together between the subject pool. So you start having that same brain synchronization as well. And so what that means is that, when you combine things like advanced displays together and natural gesture interaction and emotion sensing and sharing, you might get what you might call empathic teleexistence, which changes communication. And people now move from being observers to being more participants and sharing experiences together. The nature of communication changes from explicit to implicit communication, and you have more experiential activity together. So this may even, in fact, produce behavior that is better than being in face-to-face. And it sounds kind of like science fiction, but it's people are trying to make this a reality today. There's experiments being done in Japan where you can have a remote teleexistence experience where you can put a VR headset on and you can jump inside a robot body and you can perform a task. And in fact, this was science fiction. 10 years ago, there was a really bad movie called Surrogates, which showed that. I'll show you a little clip of the movie. So in this future, everybody has robots, and you go into VR and you walk around with your robot body. And because you've got a robot, the robot can do things you can't do in the real world. So here's Bruce Willis going into VR. This is now the robot Bruce Willis, and you'll see robot Bruce Willis has a full head of hair and looks really handsome and younger. And then you can go out in the real world and you can do some things like you wouldn't normally do, like, for example, jumping off a building like this person's about to do here, because you can never be hurt. But in this movie, somebody kills one of the robots, and for the first time, the person in VR also dies. And so it's kind of a mystery to try and figure out why that's happening. It's a really terrible movie, but the idea is kind of interesting. And it may sound like science fiction, but the company in Japan, Teleexistence, is doing this for real now. So you can see a person jumping into VR, and he's going to go to visit a surf shop in Hawaii, puts his VR headset on, and then in the surf shop in Hawaii, this is a teleexistence robot. It has stereo video cameras, stereo microphones for the ears, and it has touch sensors in the hands, and it can move around. So now it's providing a teleexistence experience for the person at home, and now the person can touch the board and can make a purchase. So this shows an example of what communication might be like in the future. And once we are inhabiting another person's body or another robot's body, then we can, the communication cues we share may be the same as what we do in our own bodies, and that may change significantly how we collaborate with each other. So just to finish up, I've shown you today, there's a number of growing number of collaborative AR and VR systems, but it turns out there's actually relatively few formal user studies, especially ones considering communication models. There's some existing communication models. There's 70 years of history in terms of people putting together communication models, and they can be applied to collaborative systems, and they can inform design and they can inform experiment behavior. And there are many, many directions for future research. So the communication models I've shown you aren't designed with AR in mind. So there's some research being done about designing new models. Of course, you can use those models to create new types of collaborative systems, look at new communication channels like the EEG I showed you, and also move towards like this empathic teleexistence, or looking at what happens when we inhabit other bodies, but many other directions as well. So thank you for your time. I'm happy to answer some questions, and here's also my email address. If you'd like to receive a copy of this presentation, just email me and I'll send you a copy, and I'm happy to answer some questions over email or face-to-face. I know we don't have too much time left for now, but thank you very much.
Thank you so much, Marcus. A great presentation. Manuel, are you still there? Manuel? Yes. Do you have to terminate it? I think we can go for an extra 5-10 minutes. Would that be a problem? Yeah.
Thank you so much. Sorry I spoke too long.
Thank you. Thank you so much. So thank you, Mark, and reminder, use the Discord for additional questions later. I want to thank everybody again. In case if I get disconnected, my internet has been having some problems in the past hour. Uh, so Bernardo Marcus says, amazing presentation, really enjoyed it. Question, what does Mark think are the main challenges associated with the evaluation of these types of solutions? And how can we impose current evaluation methodologies to better understand the impact of AR, VR in the communication slash collaborative process? Thanks. And the
Oh,
question in the text, if you like to read it too.
thanks. That's a great question. So there's no real challenges. So many collaborative studies we do use pretty coarse measures. So, you know, they have a measure of performance, but actually performance measures are not very good measures of communication. And then sometimes you'll have surveys. You ask people, how well do you think you communicate with somebody? But again, that's very subjective. So if you want to dig down and understand what's really happening, you need to do some low-level communication analysis, like, for example, looking at all the words that were spoken. But that takes a long time. So one of the challenges is building tools that can automatically or semi-automatically capture communication behavior. What's the words being spoken? What gestures are people making? And then there's another challenge is looking at how we can use physiological cues to measure communication state. So, for example, if we have a way to look at somebody's face with the camera, we might be able to measure the person's emotional state. Or if we're measuring their brain activity with EEG, we might be able to measure their cognitive state. So there's been almost no work has been done in that space, how you can automatically capture communication cues and how you can also look at cognitive and physiological cues to produce more objective measures of communication.
Thank you, Mark. Would anybody like to ask a question? You can just ask or raise your hand or type the text.
There's one question from Esther. They're talking about what type of facial expression type of information was a face expression sensor talking. I think she's talking about the empathic glasses. And in this case, what we had is a photo sensor around the frame of the glasses. And as you made different face expressions, the photo sensor would measure the distance between the glasses and your skin. And as you made different face expressions, the distance changed. And we used some machine learning to map that to different face expressions. You know, if you're smiling, then the corners of your eyes would crinkle up. If you're frowning, then your forehead would move. And so you can measure that by using that simple sensor. But then, of course, you know, with the Hewlett-Packard Omnicept display, they're going to have a face camera in there, so we can actually do some face tracking, which is going to be fantastic because you can get some much more reliable face expression information.
Thank you, Mark. And I may have missed some questions because my chat cleared when I got disconnected. I don't know if there's any other question in the chat, but I don't see any other question. Anybody would like to ask a question?
So I have a question. In one of your slides, you mentioned that there's a relationship between task complexity and also face-to-face, the use of face-to-face meetings. I wanted to know by task complexity, do you mean the ones that related to human, for example, I don't know, business, tourists, and all of this kind of stuff, or even it would be useful for a complex mathematical question, for example, having a 3D plots and having avatars there that explaining the question. Do you think it would be useful and increase the, I don't know, engagement or the performance of the users?
That's a good question. So that was in the context of media richness theory, and what they were saying in that theory is that you know, if you're trying to negotiate with somebody, for example, if you well, a good example is dating. You imagine you're trying to date somebody or get to know them, then you really want to do that face to face because you can look into their eye and you can see their face expression and you can know whether they're making a joke or telling the truth or lying to you or whatever else. If you try and do that, you know, on mobile apps, then the quality of the connection is not so strong. And it's the same also in in VR. I didn't have enough time to put slides in for this, but the early VR environments, like what Anthony Steed showed, the early collaborative VR environments, had people that were very crude, just blocks for their face, didn't have moving mouth, or didn't have eyes in some cases, and the communication cues they can show is very low. But now you've got companies like Facebook that are looking at how you can build photorealistic avatars that copy your face. So in that case, you might be more comfortable with doing a business negotiation or trying to date somebody in VR, as opposed to talking to a cartoon character, because there's a lot more communication cues. You can achieve that common ground much more quickly, and you can also establish empathy and trust, which is very difficult to do when you've got a cartoon character. So but then of course some tasks we don't need that. So I showed some examples of assembling Lego blocks or moving blocks around to make pictures. In that case, to achieve that task, we just need to know where the person was pointing. I didn't need to have a photorealistic avatar of the person appearing in front of me to help me with that task, because the task was so simple. You just need to be able to do the pointing for that.
Thank you.
Thank you.
Do we have additional questions for Mark?
May I ask a question?
Yes, please.
Hi, thank you, Dr. Berninghurst. I really agree with the need to, carry out communication evaluations in these collaborative AR and mixed reality systems. However, one thing that keeps haunting me is that, unlike in the real world, we normally have various means of communication channels. Normally, when we do the study, we would want to isolate them down to one communication channel. But one thing keeps worrying me is that would that hurt like the validity of the study, because we are constraining the users to just focusing on one communication cue versus the other?
Oh, that's a really interesting question. And in fact, one of the advantages of using VR is that you can do some things that you can't do in the real world. Like you gave the example of reducing the communication cues down. So for example, I showed some video of the brain synchronization, and it turns out it's a very active area of research right now in psychology to try and understand why this happens. Is it because your face is showing some micro expressions, or is it because you can make eye contact, or because you are looking at what body actions a person's doing? But if we do the same thing in VR, we can explore that, because we can change the conditions. So right now we're doing an experiment in VR looking at the role of gaze and brain synchronization, and we've got several avatars. One avatar, their eyes never move, so they never gaze at you. A second avatar maintains eye contact. A third avatar always looks away from you and never maintains eye contact. And so it's easy to do that type of experiment in VR, but you can't do it in the real world because you can't have people whose gaze is always fixed. And so what VR does allow us to do is change those communication channels. And that's important because, as you said, it may be unrealistic in the real world, but in for some tasks, some communication channels are more important than others. And until we isolate those channels out, we can't discover their relative importance. So, for example, with the study that we're doing in the brain synchronization, we have a theory that gaze is important, but until we modify the gaze on virtual avatars, we can't explore that. And then another thing that might be important is the micro expressions on the face. So maybe the next experiment we do is looking at micro expressions. So one of the benefits of VR is you can isolate those channels, and then that helps us to design better communication experiences in the real world, because we know what's the relative importance of those communication channels are. So hopefully that answers your question.
Yes, thank you.
Thank you. The question by Christina. Thanks for the great talk. Have you seen the relation to trust/accuracy of basic actions based on the amount of cues provided? If yes, does that also hold for the cues that we do not have in the real world? And I'll paste the text if you want to. The text is already pasted on the chat.
Oh, that's a very interesting question. So actually, we have done, and I didn't talk about this in the slides, but we've done another experiment on trust and looking at how we can measure trust by measuring people's physiological response. So when you've got a a virtual character, for example, that lies to you and you don't think you trust it, your heart rate changes and you can detect that. I think, but I haven't done much research on looking at how trust varies depending on the cues. I suspect as you have more communication cues being provided, and as they all start agreeing with each other, then you'll get more trust happening. So, for example, and you can see this in the real world, if somebody tells you that they're very happy, and they say they're happy, but their face has a sad expression on it, or they're crying, then you probably don't trust them that they're happy, because the visual communication cue doesn't match up with what they're telling you. But if they say they're happy and they're laughing, then you believe them and you feel that they're happy. So if we have communication cues that agree with each other, then we're more likely to believe them. So but I haven't done any experiments on that myself, but it's just my gut feeling, I would say.
Thank you, Mark. Thank you so much. It was a great presentation. I'm gonna close the